It's 8:20 a.m. Central Time. Happy to see you all here in the room as well as those online. We're going to go ahead and kick things off and do our best to stay on schedule here. So welcome everyone to LPSC 2025's Astrobiology and Exobiology session, Life, Habitability, and Biosignatures, Mars and Ocean Worlds. My name is Morgan Cable. I'm co-chair, and our other co-chair is online.
Hi, my name is Denise Buckner. I'm dialing in remote from Goddard.
And we also have our wonderful moderator here, Shelby.
Hi, you guys. My name is Shelby Osborne. I'm at the University of Arkansas Center for Space and Planetary Sciences. You probably won't be hearing from me much, so I just wanted to quickly remind everybody that there's a sanctioned code of conduct for respect and kindness, and we would like to all respect that in this session today.
All right, thank you, Shelby. So we've got a very exciting lineup of speakers today. We'll have 4 talks, 10 minutes each, and then we will have a Q&A period. So please do hold your questions until that point. And we still have a couple of extra minutes before we actually kick things off, but we can invite our first speaker, Joel Hurwitz, up to just make sure we've got the slides and everything ready to go. Joel's going to be telling us a little bit about a potential biosignature detected by Perseverance on Mars. So again, we'll make sure to remind speakers that they have 10 minutes at the 8-minute point. So when you have 2 minutes left, that's when the orange light will go on. So you do have 2 minutes at that point. If you see Shelby or I stand up, that is your signal that your 10 minutes are up. And do hold your questions until that Q&A portion, which will start at, let's see, 9:20, I believe. 9:05. 9:05 is when the Central Time is when our Q&A portion starts. Denise will also be helping to introduce the speakers today online and moderating questions as well from our virtual participants.
Do I get a bonus 2 minutes? Is that?
I think we're going to do our best to start right on time, just in case some people are dialing in a little bit late. But really looking forward to this session today, as well as the afternoon session where Shelby, our moderator, as well as a bunch of other speakers will be presenting. I have like 1 minute left.
And that means my mic is activated too.
We're all enjoying the soft chat.
Yeah.
All right, let's go ahead and introduce our first speaker. Joel Hurwitz of the Mars 2020 team is going to be telling us about the detection of a potential biosignature by Perseverance on Jezero Crater, Mars. So go ahead and take it away, Joel.
Will do. Thanks very much, Morgan. Really excited to be here on behalf of our co-author team. And I wanted to kick things off with just a quick reminder for everybody of what we mean when we say potential biosignature. This is a feature that is consistent with biological processes and that when encountered challenges us to attribute it to either inanimate or biological processes and compels us to gather more data. And the other thing I'll point out, you don't have to read this, is just the importance, as highlighted by the Mars 2020 science definition team, of the geological context in which those biosignatures or potential biosignatures reside. And as a final reminder, I'll just point out that potential biosignatures can take on a variety of flavors. They don't have to be microbial mats or stromatolites. And in fact, the things that I will describe to you today would probably fit the categories of organic, mineral, chemical, and microscale fabric and structure potential biosignatures. So let's start off with geologic context. We're here within Jezero Crater, and I'm going to zoom up to the investigation area here in Neretva Vallis, where we encountered a set of outcrops that turned out to be really interesting. They occur within the Neretva-Vallis channel, and we investigated them along our traverse in two areas named the Bright Angel outcrop and the Masonic Temple outcrop. Collectively, we now refer to these as the Bright Angel Formation. What we see from the ground when we look at images of these rocks, looking down and up the Neretva-Vallis channel and into the subsurface with our ground penetrating radar, is that the rocks that we investigated appear to fill the Neretva-Vallis channel, and they form these sort of concave upward to flatline deposits that sit atop the adjacent margin unit. And so we interpret these as being younger than the adjacent margin unit. And when we look at the detailed sedimentology and textures of these deposits, what we see is that by and large, they are made up of very fine-grained mudstones and some occurrences of conglomerates that are also matrix-rich that express a wide variety in iron oxidation state, from things that are really red to things that are less red to things that are almost completely white in color. And our interpretation of these deposits is that they are sediments deposited within a valley-confined lake system. The color properties of these mudstones are really well expressed in reflectance spectra that we get from the Mastcam Z and SuperCam instruments, which when you plot both of these data sets on band depth versus band ratio plots indicate that these rocks express a wide variation in iron-free content, from things that are very iron-3 rich to things that are very iron-3 poor, so variations in oxidation state. But uniquely, and despite those variations in iron oxidation state, these rocks are also very iron-rich compared to anything else that we have seen in the sedimentary rocks of Jezero Crater. So when we look at the chemistry of these rocks from pixel on a ternary diagram of iron, magnesium, and 50 times manganese, what you can see is that the Bright Angel Formation is very iron-rich and magnesium and manganese poor compared to anything else in the Jezero sedimentary section. And when we look at pixel XRF analyses of these rocks on another set of ternary diagrams here, the silica, alumina, calcium, sodium, potassium, iron, magnesium diagram, we also see that these mudstones are very silica. Let's see from my silica and aluminum rich. And we interpret these chemical relationships to indicate that the sources of these sediments acquired their iron, silicon, and aluminum-rich character as a result of oxidative chemical weathering in the source regions of these sediments. Okay, within these sediments, what we see are some unique redox-driven diagenetic features that are present throughout the Bright Angel Formation. Mike Tice and I are going to touch mostly on things that we saw in the Bright Angel outcrop. Adrian Brose will pick it up with things that we saw over here in the Masonic Temple outcrop area. I'm going to zoom up to one particularly representative outcrop in the Chiava Falls area. Here is the Beaver Falls workspace, and we're going to focus in on things we saw in this light-toned block of outcrop. And I'm going to zoom in just one more time here to this area where this target called Chiava Falls is located, and which we drilled into to collect our Sapphire Canyon sample. And this is what we see when we look at that target up close and personal. There's a number of textural features here that include layers of variably hydrated calcium sulfate with very coarse sand-sized olivine grains, interlayered with a reddish colored mud that when you zoom up has these interesting features in them that we've taken to calling poppy seeds and leopard spots. The poppy seeds are sort of 100 to 200 micron black to blue to greenish colored speckles. The leopard spots are reaction fronts that are bleached of their red color in their core and are rimmed by the same material as in the poppy seeds. And we can see what these things are made of when we overlay pixel chemistry on these targets, where you can see that the matrix in this RGB mixing map of iron, sulfur, and phosphorus, the matrix or the mud is iron-rich. The purple indicates that the poppy seeds and leopard spot rims are a mix of iron and phosphorus, and the interiors of the leopard spots have a kind of dull yellow to green color, indicating they're a mix of iron and sulfur. Looking at the chemistry of these features in a little bit more detail on a ternary diagram of iron, phosphorus, and calcium, what we see is that the points that are associated with poppy seeds and leopard spot rims scatter towards a position on this diagram consistent with a 3-iron, 2-phosphorus mineral, such as the ferrous iron phosphate mineral vivianite. I'm not going to go into this in any detail, but what I will point out is that these green lines here are tau plots that show the composition of the poppy seeds relative to the matrix. They are trace element enriched in nickel and zinc. Looking at the materials inside of the interior of the leopard spots and in some associated iron and sulfur-rich areas in a nearby abrasion patch, what we find is that the points in those areas scatter towards a position on this iron-sulfur calcium ternary that indicate that this is a mixture of iron and sulfur with a stoichiometry consistent with the iron sulfide mineral greigite. The X-ray backscattering properties from this material indicate that it is more likely an iron sulfide than it is an iron sulfate. And again, we see that nickel and zinc trace element enrichment. I'm going to speed up here and just point out that when we look at the mudstone here with the Sherlock-Raman instrument, we also see that there is organic matter in this mud in the form of a Raman G-band detection that is consistent with the presence of macromolecular organic carbon. And importantly, the strongest signals for that G-band are associated with the least red materials, and the places where there is no G-band, those are the reddest rocks that we've encountered. So taken together, these rocks are universally iron-rich, but they seem to express variations in iron oxidation state. And those variations in iron oxidation state seem to indicate that where things are not red, like you see in this near IR blue reflectance ratio, that's where we can infer the highest abundance of iron phosphates and iron sulfides and the strongest Raman G-band signals. And the reverse is true for things that are the most red, indicating that after deposition, 2 minutes, oxidized iron was reduced by organic matter, bleaching the rock of its red color and depositing iron phosphate and iron sulfide. Okay, very quickly, I'm just going to point out that we are trying to understand whether or not heat could have driven these redox processes between iron and iron, sulfur, and organic matter. Very briefly, I'll just say that as far as we can tell, there is no sort of coarse recrystallization of these rocks that would indicate that they were formed in association with contact metamorphic reactions or high temperature fluids. So everything seems to be consistent with low temperature processes. Okay, so my last slide here. What we have described here are organic, chemical, and mineral textural associations in the Bright Angel Formation that indicate that iron and sulfur reduction took place likely at low temperature, where ferric iron, phosphorus, and sulfate-bearing sediment reacted with organic matter to form reduced phases like vivianite and greigite. On Earth, reactions like these are commonly associated with microbially driven organic matter respiration using ferric iron and sulfate as terminal electron acceptors, such as this example from anoxic marine sediments off the coast of Taiwan from this 2014 paper. It is possible, though, that some of these reactions could also have been driven by abiotic processes. And so I'm going to come back to the definition of a potential biosignature from Dave DeMarais to say that we are compelled to gather more data on these features on the Mars 2020 side. And as a community, we should feel compelled to do a whole lot of laboratory, field, and modeling studies to try to investigate features like this in more detail and ultimately bring these samples back home so that we can reach a conclusion with regard to whether or not they were or were not formed by life. Thanks very much.
All right,
Thank
next up we have Mike Tice, who's going to be continuing on with some research from the Bright Angel workspace, looking at biotic and abiotic ways to form some of these poppy seeds and leopard spots.
Thanks. Well, I'm going to be picking up where Joel left off here. Joel just introduced poppy seeds and leopard spots as reduction features in the mudstones of the Bright Angel Formation on Mars, and made an argument that these things are possible or potential biosignatures. And that's because biological iron and sulfate reduction are plausible explanations for how they formed. But as he was also really careful to point out with his flashing arrows, abiotic mechanisms are known to produce at least some of the things that we're seeing here. And so it's really important that we understand the environmental constraints on how these things were formed and how that might have affected both kinds of mechanisms. So what I'm going to show you now is how simple chemical models help us test whether these mineral associations could form under realistic conditions for these rocks. I'll start out with a blow up of the chemical overlay that Joel provided earlier. You see here another iron, sulfur, and phosphorus map over the leopard spots and poppy seeds. What we're really going to be trying to explain here is the striking redox gradient that you get across these features. So the interiors are most reduced, at least with the leopard spots. They have slightly less reduced rims, and then they sit in more oxidized matrix. Now that gradient structure tells us two things, that plus the fact that the sulfides are the most reduced phase. It tells us that diffusion likely played a role in structuring these things. And it tells us that at the centers, there had to have been something at least as reducing as sulfide in order for these things to form. These are sharp features, sharp redox gradients. They're sub-millimeter features. That also tells you that the oxidation and reduction and mineral precipitation had to have been happening rapidly enough that diffusion didn't simply homogenize the entire system. So let's start pushing towards a model from those observations. And this is really setting up the model that I'm going to present to you the rest of the time here. So one of the first things that we do is say that mechanoate, another iron sulfide, is likely the first thing that formed instead of greekite. It precipitates more rapidly, but also it's a great precursor mineral to greekite. It converts readily to greekite later. I'm also going to assume that vivianite is the iron phosphate that forms. You could also later get partial oxidation or incorporate oxidized iron to get the mixed phase things that we see now. And even in addition to that, we assume that the siderite that we currently see in the rock formed later, either because there wasn't a lot of carbon dioxide around, or maybe even more likely because siderite precipitates more slowly than these things. Then the system actually becomes really simple, and redox is the primary thing controlling variations. So now we can use models to start to think about what might have controlled redox state in each of these cases, and especially what's the potential role of sulfide in either driving or responding to redox changes. These are the two basic cases, the two drawings over here. One case, here's the second case that we're going to consider. If the first case, we have sulfide either as dissolved hydrogen sulfide or as detrital grains added from somewhere else. The main thing here is it's not produced locally. In either case, sulfide then winds up being the primary driver of the reduction of ferric iron around the places where it's introduced. And that the resultant ferrous iron can either go into precipitating vivianite or sulfide minerals. In the second case, we start with organic matter instead, and that's the primary reductant producing both ferrous iron and sulfide. Now, the first step in both these cases, in this case, and the thing that's going on over here, iron reduction, can happen relatively quickly. It can happen abiotically at nearly any temperature that we'd consider for these rocks. But the second step in this case, sulfate reduction from organic matter, it's a different story, as you're about to see. And that's part of why we want to consider these different models. So sulfate reduction by organic matter on Earth is known to happen in two basic ways. It can happen abiotically over thousands to millions of years at temperatures of 120 to 140 degrees or higher. Or at lower temperatures, that reaction, the abiotic reaction, is so kinetically inhibited that really the only mechanism that we know of now is biologically mediated. So as Joel was arguing earlier, we don't see evidence that these rocks experience temperatures as high as 120 to 140 degrees Celsius. But in addition, I'll just mention here that there are some things that we typically see in thermochemical sulfate reducing systems on Earth that we don't see in these rocks. Things like coarse-grained dolomite or local reduction of sulfate minerals to sulfide. We don't get those here. So if we wind up saying that sulfate reduction from organic matter was an important part of forming these features, then that makes abiotic mechanisms less likely, and poppy seeds and leopard spots become maybe even more interesting as potential biosignatures. So this model is ultimately going to be about trying to get at what the ultimate reductant here is and what the role of sulfide is in forming these features. Now, the model that we built is fairly simple. Just think of a small spherical isolated zone where things are being reduced in a muddy sediment. In case one, the ultimate reductant is sulfide, and it sits here in the center and diffuses out through a small spherical shell and reduces iron as it goes. So you see iron building up, sulfide going away as it diffuses out and is oxidized. In the second case, we have organic matter locally reducing iron. Iron builds up and diffuses out. And then later on, if the iron gets used up, it switches to sulfate reduction and becomes more like this. Our assumptions, we assume that phosphate's buffered by adsorption to iron 3, so phosphate's a constant. You can relax that assumption. We've done it. It doesn't change the assumptions it doesn't change the results all that much. We assume diffusion that's similar to fine-grained sediments on Earth, and we tie it to the porosity. Maybe most interesting, we assume that the iron 3 reduction and the sulfate reduction rates are equal to the maximum biological rates that we observe in sediments on Earth. That allows us to test for plausibility of biological explanations, but also gives us sort of the best case scenario for the abiotic reactions. They're generally going to be slower. And then finally, we don't model precipitation explicitly, but we assume the iron sulfide precipitation is very fast, that vivianite precipitation is slower. We just look for where that's saturated. Okay, so here are some results from that. It turns out that precipitating vivianite in poppy seed-sized structures is really hard when you do that from sulfide. You require a lot of dissolved phosphate to make that happen, and phosphate concentrations that are pretty unrealistic for sediments like this, especially in iron-rich sediments where there's dissolved calcium in the pore fluids. The reason that is because as you build up iron, that actually produces an iron wall that makes it difficult to diffuse sulfide out and reduce more iron, and it also competes with vivianite precipitation by consuming some iron to make sulfide. So it turns out making poppy seeds is probably chemically unrealistic, physically unrealistic for if you try to drive it by sulfide alone. Organic matter is a different story. It doesn't suffer from the iron wall that sulfide does. And in fact, the model that we've got predicts that you get features like poppy seeds for conditions that are relatively alkaline, relatively shallow burial, and with phosphate concentrations that you see regularly in sediments on Earth. So this seems to be a good physically and chemically plausible way of making these things, the poppy seeds. It also gives you an advantage because if you shift over to sulfate reduction after iron reduction, that takes place in an environment where you've already built up ferrous iron in the pore fluids. So when you start making sulfide in these things and starts replacing some vivianite, you export phosphate out to the surrounding pore fluids where it meets the iron that you've already built up and starts to make vivianite and rims around the sulfide, just like in poppy seeds. So it's really this two-step process that winds up being important in these models for making the full suite of features that we see. If you don't do the iron reduction first, you don't get the poppy seeds. If you don't do the sulfate reduction later, you don't get the leopard spots. And I'll let you look at this, but that is really what we think is the most important thing here. Sulfide production alone can't drive the entire process. It really needs to be something more like the biological sequence of iron reduction followed by sulfate reduction in order to get the full textural association of minerals.
All right, thank you, Mike. Our next speaker is Adrian Brose, who's going to be telling us more about these green reduction spots.
All right, good morning, everyone. I'm Adrian. I'm a postdoc at Purdue, and on behalf of all of our incredible co-authors here and the Mars 2020 science and engineering teams, I'm excited to share with you today some additional results from the Bright Angel Formation in Jezero Crater. So as Joel nicely outlined, the Bright Angel Formation is here in the Neretva-Vallis channel, and Perseverance explored this area in July and August of 2024. The Bright Angel Formation is composed of a northern and southern component. Joel and Mike were speaking of the northern component here, that Chiava Falls Walhalla Glades members, and today we'll focus on the southern extent or exposure of the Bright Angel Formation here at the Mount Spoonhead member, where we see these really enigmatic and interesting redox features, which will be the focus of the talk today. Perseverance explored the red-hued mudstones and conglomerates at two locations, the Mount Spoonhead outcrop, which later became the namesake for the Mount Spoonhead member of the Bright Angel Formation, and then further up section at the Wallace Butte workspace, where we performed an abrasion patch at the Malgosa Crest abrasion. The Mount Spoonhead member shows these really remarkable intercalated mudstones and conglomerates with some possible mud clasts here, likely fluvio or lacustrine. Here's our Mastcam-Z multispectral images. On the right, our decorrelation stretch, or DCS, which is just a mathematical technique to enhance subtle color differences in these images, showing really remarkable and striking, exotic, if you will, fine-grained conglomerates. The calcium sulfate component in the mudstones in particular had this really unique geometry and distribution with this thin, wispy, vein-like form that followed, in some cases, polygonally fractured surfaces that was accompanied by these diffuse, smallish, 2 millimeter-ish so spots in the bulk matrix. And altogether, we realized very rapidly that these rocks were likely subject to a complex diagenetic history, likely with interactions with liquid water. Another form of the calcium sulfate phases, which we saw had this really unique crystal form that was almost rosette-like or bladed here at the Mount Spoonhead member, roughly 1 millimeter or 2 in diameter. The Mount Spoonhead member, looking at some chemostratigraphy now as we work through our understanding of the geochemical history of these rocks. These are showing supercam laser-induced breakdown spectroscopy points, or LIBS points, on bedrock, highlighting some of our alteration indices as a function of elevation, showing that there's definitely evidence of open system aqueous alteration here, CIA values exceeding 70 in some points, along with our mafic index of alteration, MIAO, and our index of lateralization, more or less a measure of iron gain in these sediments, showing distinct stratigraphic trends, which perhaps could indicate something like in situ oxidative top-down weathering. But again, caution is necessary here because, of course, the detrital component, the muds from the source regions of these clays could have, for example, inflated some of these alteration indices. So we're working through these results now, but with respect to the alteration mineralogies that we see, Lucia Mondon will be speaking about this on Thursday at 3:40 p.m. In Ballroom 6, showing likely the presence of aluminum-rich clays such as illite or montmorillonite, other really interesting alteration phases, octagonite and jarosite also detected in bedrock around this same workspace. Zooming in now on the textures and features of the Malgosa Crest workspace. The Wallace Butte workspace here showing the really red-hued nature of the Malgosa Crest abrasion patch, which we performed here. As Joel showed in this plot, these rocks, the green triangles here on this band depth parameter plot is showing that the Malgosa Crest abrasion with the green triangles in the far upper right corner of the graph, these rocks are by far and wide the most oxidized rocks that we've seen yet on Mars 2020. They plot similarly to lab spectra on the way to hematite and other strongly oxidized phases. Zooming in now on these really interesting green spots, which will be the focus of the remainder of the talk here. We imaged these spots, which were somewhat abundant in the Malgosa Crest abrasion with our Mastcam-Z's multispectral capability, and showed that in the band depth parameter maps on the right that Along with the light-toned calcium sulfate phase in these abrasion patches, the green spots themselves have this really depleted 528 nanometer band depth value, indicating that they are likely depleted in iron 3+ relative to the red bedrock which they reside in. Zooming in now on some of the striking morphologies of these spots themselves, they show these dark toned cores with sub-rounded to filamentous morphology, sub-rounded cores with this light tone, in some cases like Kermit green halo. In other cases, this appears to drape and or obscure the light tone calcium sulfate phase here, suggesting some possible association. Some of these striking features have this light toned irregular halo that rims this, again, dark toned, in some cases filamentous dark material in the cores of these. Altogether, unlike something like a transported olivine clast or other, a detrital source for these spots, this suggests these features likely formed in situ. Some of the larger spots on the order of 2 millimeters in diameter on their long axis show these really striking connected, branching, almost sub-rounded to filamentous dark tone cores, again rimmed by this light toned green phase, which appears in some cases again to be touching or adjacent to the calcium sulfate phase in this abrasion patch. However, due to engineering constraints, we don't have any idea what these spots are composed of. We did not analyze their direct composition with any proxy instruments, so their composition largely remains a mystery. But if these spots are similar to terrestrial reduction spots, then the cores could be composed of heavy metals or metalloids, things like uranium, vanadium, nickel, selenium, copper, lead, or sulfides, organics, or other organometallic complexes, for example. And so to contextualize these rocks with analog materials from Earth, we're beginning some comparisons with terrestrial, quote, red beds, which are just red-hued clastic sedimentary rocks. Here are some examples of red bed paleosols from the Triassic and some examples from the Mesoproterozoic, which perhaps before the evolution of land plants might be more relevant for some of our comparisons here with Mars. Precambrian terrestrial examples often have these spheroidal reduction spots that are attributed to low temperature microbial reduction of iron and or sulfur during burial diagenesis at a variety of depths from at the surface to kilometers in depth. And the processes that form the reduction spots at Malgosa Crest may also have formed the leopard spots at Chiava Falls, but it's also possible that may be the reason why we didn't detect as strong or a distinct organic G-band in the Raman spectra at the red Malgosa Crest abrasion patch could be due to instrument level stuff like iron interfering with the spectral response on the Sherlock instrument. Or it could be the case that the organics were there, but they were oxidized away by a later diagenetic event. And so we're still exploring some of these possibilities to try to disentangle what is going on here. But what is clear is that within the local environments of the Bright Angel Formation, there were likely multiple habitable sub-environments, something akin to like a lacustrine transitioning to a lake margin environment, for example. And two of these environments show, quote, potential biosignatures with different properties. As Joel alluded to nicely, the mineral phases of the Bright Angel Formation are finely crystalline to amorphous, seen here in basically the dark patches in these pixel diffraction maps on all of the abrasion patches from Bright Angel. These rocks are weakly diffracting, and so this indicates that perhaps they were never heated or recrystallized or porphyroblasts or any sort of contact metamorphic phases that might have driven thermochemical reduction to form some of these spots. And so this currently is our strongest line of evidence against an abiotic thermochemical reduction process for sulfur. So there's some things we know, and there's obviously a lot we do not know about these spots. And so in summary, some of the major highlights here, bullet point 3, the green spots themselves, we have quantitative analysis from the Mastcamz instrument showing that these are depleted in iron 3+ relative to the bedrock in which they reside in, which qualifies them based on terrestrial definition as reduction spots. And so there's also strong evidence of open system aqueous alteration and similarities with red beds from Earth suggest these environments were likely habitable when they formed. We don't know their composition of these spots though, and whether there was truly, maybe a lower temperature heating event, which wouldn't have necessarily messed up the crystallinity, but could have driven the reduction process. And then more importantly, the current geologic framework for understanding the geologic context of Bright Angel is kind of evolving still. And so these could be really old rocks or really young rocks, and we're still trying to work on all of these possibilities. Additional in situ analyses and sample return to Earth is ultimately required to further test or refute some of the hypotheses for these enigmatic features. And so with that, I will look forward to any questions. Thank you.
Thanks, Adrian. Next up, we have Teresa Fernaro, who's going to be discussing some work that she's done with laboratory analog studies regarding the organic interpretation of some Sherlock Raman features in the crater floor of Jezero.
Can you hear me well? May I have a sound check? Can you hear me?
Yes, you sound great in the room. Go ahead.
Thank you. So, hello everybody. I am Teresa Fornaro from the Italian National Institute for Astrophysics. Next slide, please. Okay, so in the past few years, my research has focused on investigating the astrobiological relevance of the samples analyzed by the NASA Mars 2020 Perseverance rover while exploring the Jezero crater, a 45-kilometer wide basin that once preceded Pioneer Lake, and from which the river collected rocks to be returned to Earth through the Mars Sample Return campaign. Next slide, please. Detection of organic matter is key to assess past habitability and identify potential biosignatures. And the main instrument of our Perseverance capable of detecting organic matter is SHEDM, the UPV random fluorescence spectrometer, which detects and classifies organics and minerals by generating UPV excited random fluorescence spectral maps displayed on high-resolution monochromatic images registered to color context images to correlate composition and texture. And please, fluorescence is very sensitive, and in fact, it has been observed a lot in the igneous rocks on the crater floor. I can see the next slide. Can you go ahead? Next slide, please. All right. So, igneous rocks on the crater floor show detected a variety of fluorescence features that might be consistent with the emission by single ring aromatics and polycyclic aromatic hydrocarbons. However, fluorescence is not very diagnostic, and inorganic sources like cerium, plus, and phosphates and sulfates can also produce similar luminescence. Raman, on the other hand, is 10 to 5 times less sensitive than fluorescence, but can be much more diagnostic. Next slide, please. In the igneous rocks of the crater floor, Sherlock detected 4 points in the quartier target of the Cedar Formation, with precise Raman peaks at 1500, 1500, and 6050 wave numbers associated with sulfates, which could be attributed to single and double carbon-carbon stretching vibrations or nitrates. And these are correlated with the fluorescence doublet at 303, 325 nanometers, which could be consistent with aromatic organics or with cerium 2+ within sulfates. Sherlock also detected 1 point in another target, point result of the Mars formation, with a Raman peak of 1597 wave numbers associated with carbonates and silicates, which could be due to mathematical carbon graphite G band based on similarities with the Martian meteorite SIU 008, which is a calibration target on board the rover. And the special correlation between these detections and minerals that have undergone substantial aqueous processing, such as that organic molecules may have been previously deposited or synthesized within these altered volcanic materials within the crater floor. Next slide, please. In this work, we focus in particular on Perthia, the breakup patch of the eastern area from which the Arabian and Malay coasts were taken. And we wanted to determine whether these features in the quartier target indicate organics and also elucidate the mechanisms that may have produced them. Next slide, please. So our approach was to prepare carbon sulfate ion samples and characterize them with Sherlock-like instruments to assess whether organics and sulfates could produce signals in the regions of interest. Then we use both abiotic compounds and organic compounds of potential biotic origin. Next, please. And the comparison between laboratory data set and quantitative of observation show that different types of aromatic organics and servants with fixed activity in plants, a single and double carbon structuring bands at a variety of positions within the regions of interest. No one of the classic organosulfate analogs exhibits fluorescence resembling the colloquially fluorescence double, which further corroborates the hypothesis that the fluorescence double might have an inorganic origin. However, the polycyclic aromatic hydrocarbons 9-methyl-anthrazine and the dihydroxynonylphenol in sulfate match the raw features of influence and fluoresce mostly outside the shell region, which may be consistent with the inorganic hypothesis of the colloquially fluorescence double, and illustrates that similar types of three-tubing aromatic organic molecules could be present in the. Next slide, please. So now until the best match in terms of peak positions is observed with the 1,3-dihydroxynonylphenol, while the best match in terms of peak power ratio is obtained with the 9-methyl-anthrazine. And this indicates that the remaining types of PIHs like the 9-methyl-anthrazine and 1,3-dihydroxynonylphenol in sulfate could account for the most intense components of both particular features of interest. And observed structure shifts may be consistent with differences in molecular structures and differences in the functional matrix present in quartier, which is not just pure sulfates, and also the presence of a multiplicity of similar organics as expected in national samples, which also may affect peak positions. The organics used in this study obviously are not exclusive, so that's why we're focusing on regions of interest instead of exact peak positions. Next slide, please. The main sulfates present in quartier exhibits minor bands in the regions of interest as well, but their positions on the specific measure very much. We have seen structure shifts that are very large, from 40 to 100 ring numbers, and peak heights for these minor sulfate bands that are much lower, 2 to 13 times lower than quartier's features of interest. Next slide, please. A final confirmation that the 6040 ring number feature is not a word of banding mode of a very sulfate is that rather random observations of sulfates with similar levels of hydration do not exhibit a similar moment. Next slide, please. And several lines of evidence suggest an igneous formation of these PIHs and sulfates in quartier. First of all, these features have been observed in recently altered polyclimate in the Silla formation. The similar association of organic carbon within magmatic minerals has already been found in micrometeorites. The location of these features of interest would suggest accumulation of organics in pores of the igneous rocks, which will be consistent with the physical structural synthesis from trapped magnetic phases catalyzed by iron oxides that are present in quartier. And such PIHs endogenously synthesized monomers through igneous processes might have been preserved by sulfates precipitated as consequence of reconcentration of the igneous rocks. Next slide, please. So in conclusion, Sherlock detected these complex Raman features in spectral ranges relevant to organics in association with sulfates in the particular target of the G0.4. And actually, we have observed the same features also in another target of the Fanta, Pilomonte. Comparison laboratory neurons indicate that the Raman features of interest might have some organic contributions from a mixture of polycyclic aromatic hydrocarbons like methylanthracenes and dihydroxynonylphenols that do not produce fluorescence in the range detectable by Shem. Other structurally similar PIHs not tested here may provide a similar match, and that explains the multiple components of the broad features observed in quartier. Further vegetative work will also investigate other possible inorganic contributions to these multi-component Raman features of interest. The presence of these features in igneous rocks suggests an endogenous igneous formation process for PIHs in quartier, and their association with sulfates suggests salt-mediated revolution, which is consistent with studies on micrometeorites and observations from Cape Crater, and also reinforces the hypothesis that sulfates could be crucial in the preservation and transport of organic molecules in the microenvironment, and could have played a significant role in the Martian carbon cycle, influencing the availability and cycling of carbon compounds necessary for life. So we look forward to have this course on point, because in-depth analysis of this course could reveal important details about the Martian carbon cycle and the astrobiological relevance of these samples. And I thank you for your attention, and next slide.
All right. Thank you, Teresa, as well as all of our speakers. We're now starting the first Q&A portion, so I'd like to invite our speakers up to this stage. For those of you who are asking questions online, we have 2 microphones here at the front. Please do introduce yourself and give your affiliation. And if your question is directed towards a particular speaker, please do bring up their name. We'll start with someone in the room, and then we'll alternate with questions online.
Good morning. My name is Liliana Lefticaru. I'm from Southern Illinois University, and I have 2 thoughts or questions. So the first one is, do you have any idea where the high phosphate fluids come from? Because they are not so usual, or maybe they are usual. I don't know. And the second question is, what range of clay minerals did you detect it in these assemblages? Thank you.
Yeah, the phosphorus concentration, we believe, is delivered as phosphate adsorbed on iron 3 oxide and clay-rich sediment grains. So phosphate's a common adsorbate on fine-grained sediment. If you look at the mudstone matrix outside of the poppy seeds, it's actually got quite elevated total phosphorus concentrations of order sort of half-weight.
Variations in shape and embayments and things to see if that helps us to identify where reactions were taking place by things diffusing and meeting each other. So that's something we're still looking at, but the size really does matter quite a bit.
And just comparisons with terrestrial analog reduction spots might be useful here for this question as well. There's many examples in the terrestrial literature of perfectly concentric reduction spots that a lot of times are attributed to formation through either a well consolidated, lithified, deeply buried sediment, such that it happens during late burial diagenesis, for example, under like a kilometer of overburden. But other examples in the literature that are more irregular rather than spheroidal are often attributed to, differences in porosity, permeability, but perhaps this could also be telling us something about the depth of burial being less shallow than some of these more deeply buried terrestrial examples. But we're still working through these comparisons, but I think it still could tell us something about the burial history of these rocks.
Kaushik Mitra, UT San Antonio. My question is primarily for Adrian and Joel, and might also have the answer. It's pertaining to the green reduction spots. So my question is 2 parts. So what are those green reduction spots? Are they like greenolite kind of species or green rust? And what is actually, so are they coming by the reduction of the red, like the red iron oxides, which is like slightly, or are they going from iron, like are the green things turning into the red or the other way around?
Thanks, Kaushik. That's a great question. I think a simple answer maybe to start would be we don't know their composition. We did not perform a proximity science analysis on this. Unfortunately, they're kind of the biggest examples. The best ones were in the very corner of the abrasion patch, and it was kind of dangerous to do stuff with the arm. And so their composition, as we indicated, remains a mystery. So green rust, greenolite, other vanadium-bearing micaceous minerals like roscoelite, for example, is another candidate for the terrestrial analogs at least. But yeah, we don't really know what they're composed of. And so then I guess this is sort of the chicken and the egg thing. Was the green there first? Was it reduced? I think our ongoing working hypothesis is that this was initially like a red hued matrix with either sedimentary organics or some other point source reductant that probably catalyzed the in situ reduction of iron from 3+ to 2+ and other mineral phases, making the spots bleach maybe first and then green after some of those later phases form. So that's obviously just one model. Maybe these things were green to start and got greener or something. And so I think there's multiple possibilities that, I don't know, based on our limited data set currently, I don't know if maybe we'll come up with a better story at some point, but we have pretty limited data is ultimately the message here. Yeah, thanks.
Although they do sit side by side with what appear to be ripped up mudstones that have basically the same composition as the red matrix, but have iron leached rims, and elemental distributions suggest that those rims were derived by reducing the clasts. And so I think it makes a lot of sense that the red would have started out first, and then you get different expressions of reduction in things that we see side by side in the same current conglomerate.
All right, we have time for one quick. Oh, Joel, sorry. Are you gonna?
No, go ahead.
Okay, we have time for one more quick question. Apologies to those in the room. This one is online. Denise?
Yeah, this question is for Teresa. So from this work, do you expect that if there are other types of organics that are adsorbed or entrained within sulfates, they could also cause shifts in the Raman parameters for some of those features, like CC stretching for aliphatic compounds or something with organic acids? And if so, are there specific regions of the Raman spectra from the sulfate observations on Jezero so far that you're looking at?
Yeah, definitely. We would expect MCPs or units as you see in natural samples, and this could affect the positions, and this could also explain the broadness of the feature that we see in Cartier and also in Paramount at the same time. These features are multi-component, so what we have observed with this organoid sulfate yellow work is that there are some classes or units like these PIHs that I presented that can explain the most prominent components of these broad and complex features. But of course, we cannot exclude that there are other organics that we have not tested that can be contributing. We cannot exclude that there are also other inorganic species that might contribute. That are intermixed with the sulfates. So, I mean, our observation so far with this work in particular is that we are pretty sure that there is inorganic components, plus other things that we look forward to understand more with other experiments that we are going to do in the future.
Thank you.
All right,
And we'll go.
Yes, go ahead,
Sorry.
Denise.
We'll go ahead and move on to our next session, continuing on with the Mars theme. We have up next Aditya Kohler, who's going to be discussing photosynthesis on Mars within snow and ice and the search for Mars in mid-latitude ice.
And let's have one more round of applause for our speakers from the first session. Thank you.
Yeah, thanks so much. Let's see if this works. Okay. Yeah, so I'm going to be talking about whether photosynthesis can happen on Mars within ice today, and how that pertains to the search for life, again, in mid-latitude ice today. So as you know, on Earth, we're lucky we have an effective ozone shield until the fluorocarbon cans come out, that is. And what this can lead to is essentially we're protected at the surface from harmful UV radiation. And so in the Arctic and Antarctic regions, because ice is translucent to solar radiation, if there's any dark dust or sediment at the surface, it can actually heat up, especially compared to the surrounding ice, melt through the ice and form a video that I'm sure won't play. Yeah, so hopefully, okay, so we can imagine there's some dark dust and sediment on ice, it heats up, and then it melts through the ice, forming a pool of liquid water. And then a lid forms at the surface. So imagine an ice lid that freezes over. So you can sort of see that here. A translucent ice lid. Ah, it's playing. Thank you. Or thank you. And okay, so there's a frozen ice lid, there's liquid underneath, and there's dark sediment inside. And what happens is, this is a summertime situation where there's liquid below ice, and they're called these cryoconite holes. And things like cyanobacteria come alive during the summer. And then in the winter, everything freezes over and they go dormant until the next summer. And this is a cool video of someone sticking a camera in. So on Mars, though, there's basically no effective ozone shield. And so there's 30% more harmful ultraviolet radiation at the surface. And so we're trying to see if the mid-latitude ice exposures we've been finding can provide like a refugia for life on Mars today. So on Mars, we actually, over the last 5-6 years, we've been finding ice exposed at low mid-latitude. So as low as 33 south, that's the lowest we've ever detected. So here's an example. So this is a false color image at the red sort of wavelength of a pole-facing slope. So it's a triple crater. I've kind of cropped out the side ones. And people have been calling this thing called the mantle, which are these sort of features stuck on top of the rock underneath. And often they're associated with gullies. So we can zoom in a little further. And essentially what they are debris-covered glaciers, like we see on Earth. And you can sort of discern patches of water ice being exposed in these glaciers as the overlying material slumps down. So I'll zoom into this one. And so here is the rock underneath. This is a debris-covered glacier that on the steep slopes, the overlying material is actually slumped down, expose the ice on the inside. And you can see these thermal contraction polygons that form when there's ice below the surface, heating up and contracting to crack the surface. So we've been finding these all across the mid-latitudes. There's a student at ASU, Sarah Bronish, who's actually mapping them globally. But there's lots of examples. And now we're trying to see if there's enough sunlight, the good kind, which is the photosynthetically active region, and I'll get to what wavelengths that is, as well as can the ice and the dust block out the harmful UV. So to do that, you have to look at the optical properties of both materials, water ice and dust. So here is this thing called the imaginary index refraction, which is basically how much light is absorbed. Notice it's on a log scale, more absorption and less absorption. And on the x-axis, we have wavelength. So here's blue, green, and red. The UV is between 0.2 and 0.4. And you'll notice, first of all, there's a big difference. Water ice, especially at the visible wavelengths where solar radiation peaks, is very weakly absorbing compared to dust. And you see this on Earth as well. I'm sure when it snows, it's bright white. A few days later, it turns to black. Turns out a tiny amount of dust, because of how strongly absorbing it is, can make a big difference in how dark it is. So you could take home some black snow and melt it, and you probably get less than 1% dark material, whether that's black carbon or dust. And it's the same on Mars. So Mars dust is about 9 orders of magnitude more absorbing at these visible wavelengths. So a tiny amount of dust can make a big difference in darkening a mixture. And that's also why ice is fairly transparent, but dust is opaque. And so what we did is, this paper was published 5 months ago, and we developed a one-dimensional radiative transfer model for dusty snow, foreign and glacier ice on Mars, and the Earth uses this thing called the Delta-Eddington method that's been used on Earth for the last 45 years. And we can basically do vertically heterogeneous layers of snow, ice, and liquid water, and with dust or without dust. And of course, the model is untrustworthy until you actually test it. So we found this cool set of measurements from Greenland, where they basically stuck a radiation sensor to measure the irradiance, the energy at different wavelengths, at the surface and at different depths within the ice. Here's the ice in question. It's basically glacier ice, so snow that's been compressed until it only has air in the form of bubbles inside, which could be the case on Mars because the snow is pretty old. And here's what they measured. So they measured the sunlight at the surface. Here's, again, blue, green, red. And there's a bunch of it, obviously. And the solid lines will be measured. And then they measured at 12 centimeters. So again, here's wavelength and here's energy. The blue line is what they measured. The dashed line is what our model could reproduce. And I'll keep stepping through. Essentially, at 77 centimeters, so almost down to a meter, there's significant amounts of energy still penetrating through ice. And there's more energy through ice than in snow because there's less scattering, less reflection, basically at each ice grain. So there's a significant amount of energy still going into the ice. A lot of models make some assumptions or simplifications. where they'll assume, instead of doing the spectral calculation, you just assume one value. If you do that, there's large errors you can get where you can underestimate or overestimate, compare the blue line to the horizontal black line. So that's a big issue. And we're trying to account for the spectral variation to see if photosynthesis can occur. So here's kind of the result. So another potentially confusing plot. So here's the UV again, between 0.2 to 0.4. And then here's the photosynthetically active radiation, which is between 0.4 to 0.7. And we're trying to show you how much solar radiation is available for photosynthesis in the colors versus depth. So notice this goes to 7 meters. And blue light, and this is why ice is blue when it has nothing else in it, goes down to about 3 meters in this case when there's no dust. But harmful UV radiation also gets down to about 2 meters when there's no dust. And we know Mars is a dusty place. The ice we see exposed, people say it's clean. It is clean, but by terrestrial standards, it's kind of dirty. It has small amounts of dust. And remember, small amounts of dust make a big difference. So if we add a small amount of dust, 0.01% dust, this changes dramatically. We can now only go from 0 to 40 centimeters. Remember, the last one was 700 centimeters. So we reduced by an order of magnitude just by adding a small amount of dust. Also now, remember that the dust is strongly absorbing at the UV. So now we're getting less light down at UV, which is good if we're looking for photosynthesis. But there's still light at about 25 centimeters for photosynthesis to occur. So that's good. And now let's see if you add a little more dust. This gets deeper, shallower, sorry, where now the UV light is only going down to a few centimeters, whereas the photosynthetic light is getting down to maybe 5 centimeters. So again, accounting for this dust and the spectral variation is very important. And what this can lead to are these radiatively habitable zones. And so this is for, if you vary the amount of dust versus depth, the black line is showing the DNA damage limit. So anything above that is not a good place for life to be, but all the green areas are in between where there's enough light for photosynthesis and where there's the UV has been attenuated. And then this is also dependent on the ice grain size, because as the grains get larger, the chance of being absorbed increases, but you can actually penetrate deeper. So as the grains get larger, the depth increases. And so turns out for small amounts of dust, you can have these radiatively habitable zones on centimeter scales, if it's cleaner on meter scales. But photosynthesis also requires liquid. And so here's an interesting place where on Earth it's rare because usually there's snow at the surface, but in Antarctica and these places, it's so windy that the snow gets swept off. And so they were walking along and they noticed, oh, it's dry at the surface, but there's actually liquid underneath us. So they used a chainsaw to expose subsurface melting. And it's again due to sunlight penetrating into the surface. So here are the temperatures they measured. So it was about -3 below the surface, but it's actually melting, sorry, -3 at the surface, but melting below the surface. And so you have ice, liquid, and ice. And we're modeling this. And come see my poster on Thursday for more about this, where we're developing a model for the energy and mass balance. And so these are measurements of temperature in red. And the black line, the black line is our model that we're developing. And we're testing it again on Earth before we apply it to Mars, because there's no constraints on Mars to check if our model is working. But it's interesting that this process does happen on the Earth as an analog for Mars. And to summarize, they are radiatively habitable zones on Mars today, within a few centimeters or meters. Solar radiation can penetrate pretty deeply, can melt the ice. And we believe mid-latitude exposures are the most easily accessible places to find life on Mars today. So we should go there. Yeah.
All right. All right, our next speaker is Carlos Garibicas, and he will be telling us about thermal physical characterization of the Martian subsurface. And a quick reminder to speakers who are up next, please do stop by the tech station to be able to get your microphone.
Okay.
All right, take it away.
Thank you so much. So I'm Carlos Garibicas, currently a postdoc at Louisiana State University, Geology and Geophysics. And let's start with some background on this project. So before I started at LSU, I was actually working with Deanne Rogers at Stony Brook University And we sat down and had a bit of a conversation about how we can do thermal physics for habitability. She mentioned that she worked on a project for a report in 2021 for the National Academies of Sciences, where they calculated temperature threshold values at subsurfaces on Mars. So the figure that you're seeing on the left here is sort of a latitude versus temperature plot. On Mars, the longitude that you're seeing here is 0 degrees, and the different temperature curves are different model runs for different thermal inertias, and I'll go into thermal inertia in just a second. But the point of this plot is to demonstrate, especially by the dashed lines that you're seeing on the plot, is that there are specific regions on the subsurface of Mars that reach temperature thresholds that are necessary or are useful for life survivability or microbial life survivability. You will notice that there are 2 dashed lines. I will talk about that in just a second as well. But there are regions, at the very least, according to this report, that allow for life to live. These are diurnally average temperatures, so we decided to scale this further out. So the general hypothesis of this project is depicted on this figure right here. So on Mars, you have several temperature regimes that operate in the subsurface. You have insolation that operates in the shallower region. Insolation varies in the scale of days and seasons based on, orbit. And then you have the geothermal contribution in the deeper subsurface of Mars. Now, the variability of the geologic geothermal fluxes vary on the scale of geologic eras or periods. And so to completely assess the thermal environment in this region, we need to assess both the geothermal and the insolation of the subsurface. And you will notice that I labeled ideal microbial habitable zones. So the blue temperature curve is essentially temperature at depth. And at that region where there's connection between insolation and geothermal, that's the ideal region for possible microbial survivability. Now, thankfully, we have data to be able to assess both of these locations. We have data to assess the insolation variables that we have in the shallower subsurface. And we also have gamma ray spectroscopy that can give us an indication of the radioactive elements that exist in the subsurface. Actually, Caitlin Fursell, who's currently a grad student at ASU, conducted a study in 2023 where she actually calculated the geothermal flux the geothermal fluxes on Mars in the subsurface using gamma ray spectroscopy. Now we have geothermal data. We need to get thermal data or insolation data, and we extracted this from THEMIS, TESS, or MCS, or all of them, to assess the thermophysical properties of the insolation flux dominant part of the subsurface. With these 2 data sets, we can actually input them into a thermal model. In this case, we're using the numerical thermal model KRC to compute the subsurface temperatures. The model takes into consideration thermal inertia, which is this very nice equation you see here. It was created by Hugh Kiefer in 2013. And you can input thermal inertia, this value that I said I was going to talk about, into the model as well as geothermal fluxes. Now, thermal inertia is proportional to a material's thermal conductivity, bulk density, and specific heat capacity. Higher thermal inertia means more heat can be held by the material. Think rocks versus sand. Rocks will have higher thermal inertia than sand. So with the model and the data, we then approached a region that has been characterized at depth to be homogeneous on Mars. There's this paper that came out in 2024 by Waters et al. That found that at the Medusa Fossae Formation, there are deposits that are 300 to 600 meters deep. So what this means in thermophysical data is that they're homogeneous. And we can use a single value of thermal inertia for a preliminary study. And that's exactly what we did. So what you're looking at right now on the right at the bottom is a temperature depth profile where the horizontal axis is temperature and the vertical is depth, where depth increases towards the bottom of the plot. The red curve, solid curve, is the calculated or computed temperature curve. And the dashed lines represent specific thresholds that have been established by different communities in regards to microbial survivability. So 245 was established by the Planetary Protection Committee, the Planet Protection Group at COSPAR. They said that 245, based on Earth-based experiments, is the threshold for microbial life to reproduce and survive. There was a study in 2004 by Price and Sowers that said that 233 is possibly an inferred temperature for microbial life to survive, not to reproduce. So for this specific study, preliminary study, we used 15 milliwatts per meter squared, and the thermal inertia of 54 standard units derived from test data. So you saw that there was going to be there were a couple of other dashed lines. You have the orange dashed lines that I didn't explain thoroughly here. So in the shallow subsurface, the insulation fluxes will have a limit to how variable they become as they go deeper into the shallow subsurface. This is dictated by the seasonal skin depth. So you can actually calculate the seasonal skin depth as a proportion of thermal inertia with other thermophysical variables. The seasonal temperature signature will dampen almost to negligible at this depth. So what happens afterwards is that the geothermal flux is the dominant temperature contribution to this part of the profile. And so this is what's being computed here on the orange curve. In the horizontal dashed line, you will see the boundary of the actual temperature insulation impact. The vertical tells you the temperature of that boundary. So interestingly enough, a study by Piquet et al. That came out in 2024 was able to calculate both thermal inertias and annual or approximate annual temperatures on Mars, and this is the map that they produced. So in order to initially validate our study, we compared this map and the temperature retreat from this map to the temperature that we computed in our model, and they matched pretty well. So it was kind of a micro success in the sense that we had at least, oh, and I forgot to say something so important, the depths. So the depths that we found for microbial life to survive at this location is between 6 to 10 meters, which pretty deep, but it's a very good start to try to understand microbial life. We were not happy with just one location, especially because payloads that are being pitched for search for life missions usually are stipulated to be penetrating at about 2 meters. So what we decided to do is we're going to expand this study to a global scale. But we're first going to start with studies that have been conducted by InSight. So work by Matt Grott, Matt Siegler, even Sylvain Pécu have been able to characterize the subsurface on the InSight part of Elysium using both models and whatever the mole could get to. And so we're going to calibrate the model that we're using to those values. So we're essentially going to calculate the temperature at the subsurface. We're then going to expand it regionally to mission locations for both current and future missions, especially Rosalind Franklin, that is going to probe into subsurface. Then we're actually going to scale it upwards towards a global scale. Now, another thing that we're going to do, and this is going to be with my collaborator at UCLA, Scott Pearl, we're actually going to do model variabilities or model output variabilities and compare it to habitability gradients here on Earth. And the idea is we're going to try to see the nuances of our results compared to actual detection of life here on Earth in the subsurface in extreme environments. So just to wrap up, because I only have less than a minute left. So the first synthesis of this study was successful in finding a subsurface temperature environment for the survivability of microbial life. We will validate it with in situ thermophysical studies. We will expand it to local, global, and regional scales. And then we will further constrain habitability on Earth extreme environments. And with that, thank you.
Thanks. And next up, we have Libby Hausrath, who's going to be discussing the astrobiological potential of clay mineral and potassium feldspar formation environments at a couple locations across Gale Crater.
Good morning. First, I would like to acknowledge my co-authors on this work. All right, so we're going to be talking about clay minerals. Why are clay minerals interesting? On Earth, oh no, I'm only going forward.
Little red button.
Okay.
Nice.
Thank you. Sorry about that. All right, so they're interesting because they preserve organic matter on Earth, which of course on Earth is largely of a biological origin. And glentoridin, which has large amounts of clay minerals, also has large amounts of sulfur-containing organics. And this is an image here from Milan et al., 2022, showing the presence of those organics. And so preservation of organic matter in potentially habitable past clay-bearing environments would be very interesting. So this, we're talking now about Gale Crater. So this is the landing ellipse for MSL Curiosity. And then it landed in 2012, and it has been roving up Mount Sharp. And you can see here the areas with the minerals detected from orbit, which contain a lot of clay minerals. Focusing in more closely here, you can see glentoridin, which has large amounts of phyllosilicates detected from origin, as well as Vera Rubin Ridge, which is in a similar stratigraphic position, but has likely undergone additional diagenesis. And these are samples collected from glentoridin and Vera Rubin Ridge, and then Duluth just beneath Vera Rubin Ridge. So ChemMin has measured the clay minerals in these samples and has detected dioctahedral smectites in all of them. So here are again, the samples listed, and then images of them here. And dioctahedral smectites are, for example, montmorillonite, betellite, and nontronite. And this is from Tu et al. 2021. So now those are samples from Vera Rubin Ridge and glentoridin. Very interestingly now, Kings Canyon, which has been collected within Geddes Vallis, also contains clay minerals and is very similar to samples from these previous locations, Vera Rubin Ridge and Duluth. And you'll hear more about this in detail this afternoon from Liz Rampey. But here is the traverse of the rover. You can see Vera Rubin Ridge here in glentoridin, and then 500 meters up section, Kings Canyon was collected from that little point there. The little red oval is shifted slightly to the left, but that's where it was collected. So a substantial distance away from these previous clay mineral bearing locations. And this is a pie chart of the mineralogy of Kings Canyon. In red here, you can see the clay mineral, which is consistent with the dioctahedral smectite montmorillonite. And in yellow there, you can see sanidine. So what can Kings Canyon and samples from Vera Rubin Ridge and glentoridin tell us about habitability? So this is an image of a classical view of habitability from Haller 2007, including raw materials, sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen, sufficient energy, light, or from a chemical gradient, solvent, liquid water, and then sufficiently clement conditions, temperature, pH, salinity, and so forth. So what can the mineral assemblages from these samples potentially tell us about habitability? So these are the samples from Vera Rubin Ridge, glentoridin, and Kings Canyon. And you can see that all of them contain dioctahedral smectites, and all but Rock Hall here contain sanidine. So the temperature ranges suggest that if these samples form together, the minerals could have formed in a habitable temperature range. So the current upper limit for terrestrial life is 122 degrees Celsius. The theoretical potential upper temperature limits for life are 150 degrees Celsius. And so this could potentially be a hydrothermal environment or with a temperature elevated due to burial. And then adularia, potassium feldspar, is often a terrestrial indicator of boiling. So here are the temperature constraints placed on these samples if they formed together of dioctahedral smectites, less than 150 degrees Celsius, serpentine about 50 to 400 degrees Celsius, and adularia 100 to 300 degrees Celsius. So we performed some modeling to determine whether the minerals are thermodynamically favored to form together. We used Geochemist Workbench, Act 2, shown there. The thermo.com database, temperatures of 100 110 and 120 degrees Celsius. And we varied parameters, including pH, the activity of aqueous silica, aqueous aluminum, potassium, and magnesium. And minerals that formed at higher temperatures than those being tested were suppressed. And so our modeling results are one of the examples of our modeling results is shown here. On the y-axis, we have the log ratio of potassium over hydrogen. And on the x-axis, we have the log activity of silica. So as you move in this direction, you have increasing silica. And as you move up, you have an increasing potassium relative to hydrogen. And what you can see is that our modeling results indicate that under varying conditions, the dioctahedral smectite betylite and microcline can coexist. So we can see those thermodynamically favored to coexist under various conditions. At lower lumen activity, serpentine was also stable, and we did not explore chemistry as a parameter here. So what can the coexistence of these minerals tell us potentially in the field, tell us about the potential astrobiology of Mars as well. So to do that, we look at the Azores here. So these are volcanic islands along the mid-Atlantic ridge here. And here we can focus in there in the Atlantic Ocean. You can see the archipelago here, and then into São Miguel Island and Fogo volcano there. And this is an image from whale coring from Ribeira Grande geothermal field in Fogo volcano in the Azores. So here we have depth in meters. Here we have temperature, and the yellow bar indicates a temperature range from 112 at the top to 163 degrees Celsius. So the top of that potentially likely being habitable. And then we have clay minerals. You can see smectite present at the top of that range, and you can see we have potassium feldspar present at the top of that range. So similar to what we observe in the samples at Kings Canyon and Vera Rubin Ridge and Glen Torridon, we see the presence of clay minerals and adularia in habitable temperatures on Earth. And this is an example of the microbial life present in hydrothermal springs at the Azores. And so the types of life that might be present and potentially preserved in these samples as well. And so, of course, what we're interested in is what kinds of biosignatures could be detected in these types of clay mineral-bearing samples. And so this is an image from Mustard et al. 2013, and you saw this list also already in Joel's talk. So we can see potential organic biosignatures, minerals, macrostructures, microstructures, and chemical and isotopic biosignatures. And for further discussion of this, the next talk by Bailey and the poster by Lena Sissel Thursday evening, abstract number 1683 will be great. So in conclusion, the potassium, feldspar, and clay minerals are detected in Glen Torridon, Vera Rubin Ridge, and Kings Canyon. Modeling suggests that these minerals could have formed together under potentially habitable temperatures, and potential field analogs indicate locations where we see these similar combinations of minerals and the types of life that could be present in these environments. And with that, I would like to thank the MSL science and engineering teams for their work that has enabled this work, NASA for funding, and thank you for your attention.
Thank you, Elizabeth. Our next and final speaker of this portion of the session is Bailey Colburn. She's going to be telling us about potential biosignatures and Mars-relevant clay minerals. So we'll keep with the clays. Please do remember to get your questions ready. We've got a Q&A button on the Zoom, or you'll be coming up to the microphones after Bailey's talk. So take it away, Bailey.
Thank you. Good morning, everyone. First, I would like to thank Libby for that great talk and for the perfect transition into my presentation. My name is Bailey Colburn. I'm a second-year PhD student at UNLV, and I'll be presenting my project titled Potential Biosignatures in Mars-Relevant Clay Minerals, a Key to Uncovering Past Life on Mars. So to begin, I would like to take us to the area of interest for this project, which is the Jezero crater. This 45-kilometer wide crater is very compelling due to its high potential for habitability and for hosting a suite of biosignatures. You see here a mineral distribution map that was developed by Gouge et al. While the whole map does provide very valuable information, I would like to draw your attention to the blue area, which is what I'm particularly interested in for my project, as it's where the magnesium-rich smectites have been found. Now, since landing in 2021, the Perseverance rover has been happily making its way through the crater, collecting samples to be sent back to Earth for detailed analysis. Now, it is very likely that clay minerals are among those samples being collected, and if ancient life ever existed on Mars, it is likely that these clay minerals will play a crucial role in preserving its signs of life. Now, here I just highlighted two samples that are likely to contain clay minerals from the sample collection. These are hazeltop and bear wallow. So now, why do we care about clay minerals? As we mentioned, clay minerals have this unique structure, which gives them this amazing ability to preserve and protect organic molecules. But organics are not the only type of biosignature that we can associate with clay minerals, as been previously mentioned. Here you can have organics, mineralogical, macro and microstructures, isotopic, and chemical biosignatures. Now, for my project, what I'm doing is I am taking a Mars-relevant clay mineral, and I am combining it with a Mars-relevant microorganism to determine if trace element, isotopic, and mineralogical biosignatures can be detectable. Today, I will be focusing on the chemical biosignature, which is why I've highlighted it here in red. Now, I'd just like to mention that studying these biosignatures and samples we have here is really important for when we get these samples back from Mars. We already have a very good idea of what to look for when searching for these potential biosignatures. So now moving forward, I'm just going to take you back a couple of steps and explain to you a little bit more about my project, starting with the biology side of things. So for this experiment, we chose Schwannella oendosus. This is a facultative iron-reducing bacterium. This means it's capable of growing in both oxic and anoxic conditions, and that it can use iron 3+ to grow. Now, these conditions are essential when looking for a potentially Mars-relevant microorganism, given the planet has very low oxygen levels and is abundant in iron 3 minerals. Now, to start, we started with an aerobic inoculum, which we grew in an LB media. And from here, I used this aerobic inoculum to inoculate my anaerobic cultures, which were grown in their specific medium, and iron citrate was used as the electron acceptor. Now, these cultures were grown to the mid-exponential phase. This essentially means we grew them to their very maximum growth curve to ensure we were adding the maximum number of cells possible into our experiments. And then in order to get a physical cell pellet that I will add to my experiments, we did centrifuge these cultures at an RPM of 8,000 for 10 minutes. And then finally, I did rinse all cell pellets 3 times to remove any impurities that were present. And future experiments will be conducted under the same conditions. However, they will be using another Mars-relevant microorganism, which is Geobacter metareducens. So now moving forward, I would like to explain to the clay mineral side of things. So as we saw in that mineral map from Gouge et al., magnesium-rich smectates are abundant in the Jezero crater. So for this project, we chose the magnesium-rich smectite saponite, which is a 2-to-1 layered phyllosilicate clay mineral. So due to its structure and its composition, this clay mineral is an excellent candidate for preserving and protecting these biosignatures. So I would first like to explain to you guys how I'm making these minerals in our lab, and I made this schematic here to help the process a little bit better. So I start here with initial solutions of magnesium chloride, aluminum chloride, and sodium metasilicate. I put them on a flask and they are stirred for 90 seconds. After that, I transfer the solution into a centrifuge tube to act as filtration. Here I do centrifuge the cultures at 9,000 RPM for 10 minutes. After which you do have the gel at the bottom here, and then my supernatant that I do discard. And then moving down here is just the gel, which I do add to my Teflon par vessel here, which is then sealed and then added to the vessel here, and it is baked at 96 hours at 230 degrees Celsius. So now moving forward, I'm going to explain to you the different biological conditions that I'm going to be using in these experiments. First, we have our abiotic control. This is the clay mineral by itself with no biological influence. Next, we have intact cells, which are whole living microorganisms. And then finally, we have lyse cells, which are cells that we physically broke apart to release the spread of different trace elements within the cell. Now, this brings me to one really important part of this project, which is the metalome. The metalome is basically just the spread of different trace elements within a cell. Now, the concentration of these elements does differ depending on the species, as it relies on the enzymatic activity of the microorganism. And now previous researchers have looked at this, and they found that when cells are lysed, they're able to release those elements into their environment. And they have found that clay minerals are actually able to trap and absorb those different trace elements. So this brings us to the really important question of, can the metalome serve as a valuable biosignature if we see an enrichment of these elements compared to our abiotic control? Now for our experiment to do cell lysis, what we did is a freeze thaw method. This involves letting those cell pellets thaw just slightly before piercing them numerous times with a needle and then refreezing them using liquid nitrogen. And this cycle was repeated numerous times. So now I'm going to explain to you guys my experimental setup. So here you see the same exact schematic that I had showed you on the previous slide. The only difference here is the addition of one of these two biological conditions as the very last step, and these are performed in triplicates. Now to help visualize this, I like to use the chocolate chip cookie analogy. So when you're making chocolate chip cookies, you follow the same recipe every single time. And that would be analogous to my clay mineral synthesis. But the only difference is the addition of the chocolate chips or the microorganisms as the very final step. So now that I've explained to you my experimental setup, I am very excited to show you some of our initial results. Starting with the SEM. So these images were taken using the Tesla and Clara at UNLV. I placed these samples on carbon tape using a gold coating. And here what we were really interested in was looking for morphological signatures and obtaining an elemental baseline map. And upon closely examining these samples, we did not see any morphological evidence of the cells using the SEM. But we do believe that the high temperature of synthesis, being 230 degrees, has destroyed any morphological evidence that we could potentially see here. But if you're interested in seeing different results with a different clay mineral, please see my colleague's poster tomorrow night's session. And now we're going to move on to the trace element side of things, and we do see a very different picture when we look at this. So here with the ICP-MS, we were looking to get the trace element biosignature. Basically, we wanted to see, do we see that enrichment with the conditions, with the biology compared to our abiotic control? So to do this with the help of our collaborators in Tennessee, we prepared our samples using nitric acid and hydrogen peroxide that were ultra pure to destroy any organics that were present. And they were sealed in a 1-to-1 mixture of hydrofluoric acid and nitric acid for 1 week at 100 degrees C. And then finally, once they were dry, the samples were digested using double distilled nitric acid to remove any fluoride. Now, before I show you the data, I just wanted to explain to you what this chart is going to be showing. So here we have concentration on the y-axis, followed by various elements on the x. And now what I'm going to be showing you is the concentration comparing my abiotic control, my clay mineral plus intact cells, my clay mineral plus lice cells, and then finally the composition of the cells by themselves, which is that metalome that we just discussed. So when you look at the first 3 elements here, we do see some enrichment, but it's not as significant if you move on here. And here we are looking at anywhere where the purple and the orange bar is higher than the blue, indicating that the lysed and intact cell condition experienced more of that element compared to the abiotic control. So now that we see this elemental enrichment here with ICP-MS, but we see no morphological evidence under the SEM, further supports the need to have a suite of biosignatures when searching for something as past life on Mars. And I also just want to mention that I think it's awesome that you can have the metalome on this graph, because by having the metalome, you can basically predict what elements you expect to be enriched in. Now, before I conclude, just a couple of quick remarks. Mars return samples have a high potential for habitability and for hosting a suite of biosignatures. And we are performing experiments under a range of temperatures and conditions to test the mineral's preservation ability and to get that potential biosignature suite. And finally, our ongoing long-term low-temperature experiments, coupled with other analysis techniques, including TEM, MC, ICP-MS, will help us strengthen this biosignature suite and fully understand this mineral's preservation ability. Before I conclude, just a couple of quick acknowledgements. First, I'd like to thank NASA for funding this project. I would like to thank all my co-authors and the UNLV crew. And as always, a special shout out to the Hasselhoff Lab Group for their endless love and support on my journey. Here's my information if you guys would like to discuss this further, and I look forward to any questions during the panel Q&A. Thank you.
Thank you. We can move on to our next speaker. I'm sorry, I'm not sure what your first name is, but...
Wait, Denise, no, we're moving to a Q&A session now.
Oh, my bad.
Yeah, no worries at all. So can we have our last 4 speakers please come up? So we've got Aditya, Carlos, Libby, and Bailey. And please come up to the mic, give us your name and affiliation, and then ask your question, and we'll alternate between those in the room and those online, starting with those in the room. So please go ahead.
I'm Janice Bishop from the SETI Institute, and I had a comment for the first speaker about the photosynthesis in the ice. And I wanted to tell you that in the Antarctic, in some of the frozen lakes where we see photosynthesis in the bottom sediments, and it's through 3 meters of ice and 20 to 30 meters of water. So I know that the modeling, you kind of talked about your experiments and you're seeing photosynthesis much deeper than the general thinking, but it can even be much deeper. And below the anoxic levels, below like 20, 25 meters, we even see anoxic formation of sulfide, biogenic sulfide forming. So there's an active community way down there deep. So there may be even more implications for your work on Mars if we use the Antarctic as an example. And I also wanted to suggest to Bailey that you try some of your synthesis at lower temperatures. I think at 236, you're altering the smectite to chlorite, which would have less of an inner layer. And maybe if you use lower temperatures, you'd be able to get more of those microbes in the inner layer region, and you might see more difference in your reactions.
Thank you for that. We actually do have those ongoing right now. They are at low temperature, at room temperature.
Sounds good.
Thank you.
Okay, I have a quick online question from Arwen Hubbard, LPSC Ambassador. Dr. Cooler, thank you for an amazing talk. I'm curious about the potential for detecting photosynthesis from orbit. Could MRO's spectrometer be used to identify chlorophyll-like pigments beneath Martian ice? And if so, how would dust affect or obscure the signal?
Thank you. And also, thank you to Janice. Gary Clow, who's one of our co-authors, has himself also seen kind of what you were talking about in these ice-covered lakes in Antarctica, like Lake Hoare. So yeah, we're definitely, and it'll be good to chat about more sort of subsurface liquid communities. And then from orbit, it'll be really difficult, mainly because of a few things. The spatial resolution, and then you would need, I think, significant amounts of microbial life to be detectable from orbit, to be, if there is even any life, we're hoping, obviously. Yeah, I don't think even on Earth that can be done in these sorts of environments, detect chlorophyll in subsurface ice that melts in the subsurface. So it'll be really challenging. I think you'd have to go there, and we should.
This is Xiaowei Wang from Cornell University, and I have a questions for Bailey. Really good, good talk. And then when you're suggesting that you are suggest that the trace element distribution can be used as a biosignature, do you think the signal from weathering, because like those metal trace elements released from weathering from lithology, can like kind of like masking that signature?
That's a good question. Thank you for that. That is something we have considered since these are laboratory experiments. Right now we're doing them in triplicate, which would help, ensure that these are being a biosignature and not being from other processes. But as far as to the weathering from the actual samples we get on Mars, I would feel like taking multiple samples would help and being able to compare to ensure that those are not trace elements that we're seeing from weathering.
Okay, thanks.
Thank you.
Hi, David Bouleste from University of Florida. So I will continue on this comment. Will you try some natural analogs to look at the biosignatures? Because when you look at hot springs and silica sinters, you're gonna have a lot of different elements that gonna sink, and according to the spring and the historical geology there, they're gonna be other like signatures, and maybe they might not be biosignatures. Do you try also isotopy maybe to help?
Yes, that's a great point. And actually, this is the first chapter of my dissertation. And as part of my third chapter, I'm actually traveling to potentially Nickel Mountain to collect samples and bring back and basically do the same idea here and compare field versus lab. Thank you.
All right, we still have about 10 minutes before our next session, and we don't have any online questions, so I'd encourage people to come in the room, and continue to submit questions online as well. Go ahead.
I'm Jung from Umeå University in Sweden. I have a question for Bailey. So you mentioned that your microbe can interact and live on iron rust, right? So why don't you consider to do your experiment with iron-rich saponite or other clay mineral instead?
Yeah, so my colleague Lena Sissel is actually using iron-rich minerals for her experiments, and I'll be comparing my magnesium-rich to her iron-rich, so then we're getting a full suite of the potential biosignatures among different clay minerals.
Hello, S.J. Ralston, they, them, Mentum at Johnson Space Center. My question is for Libby, who's hidden behind the podium right now. My question is about your stability fields in Geochemist Workbench. It looked like from the image that sort of the equilibrium between those different minerals was like a pretty narrow line. Do you know if the stability fields extend sort of beyond that, or is it like a really specific condition where they're in equilibrium with each other? So essentially, do the fields overlap, or are they just butted up against each other?
Hey, Steve, that's a great question. Yeah, and actually what was mapped was the maximum microcline. So they likely do overlap. And of course, we would also expect metastable minerals at all, but that's a great point.
Thank you.
I just have a follow-up question for Bailey. Can you spoil a bit what difference between magnesium and iron rich in your experiment?
Yes, I don't want to spill it too much because I want you to go see her poster tomorrow night. It's actually really cool. But in her high temperature experiment, she actually did see incrustation of the cells within her minerals. So even her temperature was 150 degrees C compared to my 230. So even being that different mineral with a different temperature, she was able to see evidence at high temperature compared to me.
So which one preserved better biosignature?
Well, that we're still working on, but I still have to build the suite before I answer that question for you.
I had another suggestion for Bailey. A couple decades ago, I did some experiments with montmorillonite ferrihydrate assemblages and growing photosynthetic microbes in them, and they turned out to be excellent UV shields. So perhaps that's an addendum to your experiments, to test putting them outside in the sun and see if they shield the microbes and let them live.
Thank you for that. Yeah, we've been also considering testing the survivability of the cells by themselves to see how we can see morphological evidence, kind of the same idea, but thank you for that.
Kadra Barber, University of Oklahoma. I have another question for Bailey. I was curious, you mentioned the low temperature experiments, and with these high temperature ones you did were at 96 hours, I think you said. Are you thinking of, for the low temperature ones, just lengthening the amount of time? If you're expecting any kind of proliferation for the intact cells or not? I'm just curious.
Yes, it's a good question. So the same thing that I do for my high temp, but I just don't bake it. So I make the clay mineral precursor as normal, and then I add the microorganisms and they sit for long term. We've been attempting to analyze them at the 3-month mark and also the 6-month mark. And we do hope that we will be able to see more of the evidence of the intact cells without them being destroyed with the high temperature.
Okay, thank you.
Thank you.
All right, why don't we continue to open up the floor to questions for all speakers that we've had at this point? And in the spirit of doing that, we do have a few online that are residual. So Joel and or Mike, you may want to come up to the microphone, or Adrian. This one is specifically for Mike from Mark Fox Powell. Thanks for a great talk. You considered exogenous sulfides or organic material as reductants, but is there any reason why both couldn't act together? Would that change your results?
They could. And so part of the utility of modeling is to ask, if you were to have organic matter as reductant and to independently add sulfide, what's the suite of things you would expect to get? I think one of the critical constraints is that we get sulfides with vivianite all the time, and that really suggests that they share a common reductant rather than just adding sulfide independently of wherever the vivianite was forming otherwise. So yeah, that's something that the model does allow us to consider. And it seems right now like it's more likely that they're tied together by a common reductant. But, and I want to make sure I'm understanding the question correctly, I'll also add that all the models assume that where you have sulfide with ferric iron together, that the sulfide will reduce the ferric iron.
I was actually going to ask some questions of the
Go for it. Yeah.
Current panel. So I had a question for Libby and a question for Carlos. Libby, I was curious. I think I understood correctly that the K feldspar detected is sanidine, but you were modeling microcline precipitation. Is it? Did I get that right? And does it matter? Like I was wondering whether the betalite could just be sort of like a low temperature alteration weathering product of a high temperature sanidine or something like that?
Yeah, thank you, Joel. That's a great question. And you're right that one of the caveats is that we would the if statement is if they form together. So you're certainly right. We could have detrital minerals in this system. And the terminology is difficult. And so what we would want to do, of course, is look specifically at the minerals from the hydrothermal environment in the Azores, compare that to the Chemin data. Certainly this, and again, the terminology seems to be difficult. Sometimes sanidine does seem to be used to refer to the hydrothermal high temperature, but that doesn't mean that that's what it is. There's an if statement there that if they form together, then this is true, and we could have detrital minerals.
Got it. Okay.
I hope that answers your question.
Yeah, totally. Thank you. And then, Carlos, I was the low temperature limits that you were quoting. I was just struck by how low those are, and I assume that those are like super halo tolerant bugs of some kind. And I was wondering whether, as a part of your future modeling work that you were describing with Scott, are you gonna factor, I guess, water activity and sort of specific microbiology that's required to live at those super low temperature conditions?
Yeah, so you're actually I didn't have the time to actually go through that part of the slide, but essentially what we're trying to do is we're going to evaluate cellular fitness based on conductivity and porosity that are going to be outputs from the model itself. So we're going to model some saline environments in the pore space, and yes, we are definitely. So your first threshold for habitability is temperature. Your second one will be water activity. For the Price and Sauer study, that's actually a very controversial study because it's inferred temperature threshold. They weren't, like, technically speaking, the study inferred that you could have microbial life survive at even lower temperatures. And so thinking about it in a planetary protection protocol scenario, well, if we can have microbial life survive in vacuum of space, and we have all these protocols in place for the transfer of microbial life from Earth to Mars, we're trying to find the lowest minimum threshold that we could find. So like the first order will be temperature, but then we will be testing out model outputs for other possibilities of habitability in those depths.
Thank you.
Hi, I have a question for Bailey.
Just a moment. We have one online, and then we'll do you next, if that's all right. Okay, go ahead, Denise.
Thanks. So we have a question from Eli Skulke at Los Alamos National Lab. I believe this is for Adrian from the last session. So the question is, do you have thoughts on green rust? We don't see it persist on Earth, but we do have constraints for how long it persists on an oxygen-poor planet.
Hi, thank you for the question. Yeah, I was obviously, as we indicated too, we're kind of clueless about the composition of these phases, but yeah, to your point, I think one of the potential phases that the green material could compose of reasonably based on terrestrial analogs is green rust, like a poorly crystalline phase. So as far as the range of temperatures and different phases where you might expect that stuff to find on Earth, I think it's reasonable to suggest also that that's sort of similar to what we see here. So I think ultimately we can't exclude it or exclude it any further than that, unfortunately. But yeah, thank you for the question. The mystery remains.
Hi, I'm Dipali from UT Rio Grande Valley, and I have a question for Bailey. So from your experiment, I understand that you are trying to constrain the parameters of a magnesium-rich smectite and high temperature conditions, right?
Yes.
Sorry,
Go ahead.
Yeah, to find if the biosignatures are still preserved. And rest of the conditions are not considered, right? Like pressure or composition of the atmosphere or anything, radiation or anything else.
No, we didn't consider those. We did pick the biosignatures that could persist through irradiation. So that's why we highlighted the chemical, isotopic, and mineralogical. But we are doing low temperature that I just didn't discuss here. So looking at the minerals preservation ability of those biosignatures in both high temp and low temperature experiments.
Okay, thank you.
Thank you.
All right, we have one more question online. Do you want to ask Shelby? Okay.
Okay, this question's from James Lewis from NASA Goddard. The presence of both sodium jarosite and iron magnesium carbonates with the clays in the Kings Canyon sample is really enigmatic. Good word. Do you have a sense of the relative timing of emplacement of these minerals and what this might mean for biosignature preservation?
The short answer is no, I don't have a good answer to that, but certainly it's worth looking into that a lot more to think about potential preservation of possible biosignatures in these interesting clay mineral bearing samples.
All right. I think we probably have time for one more quick question before we start our next session. So let me see if we have one from the previous. So Inga had one additional question. What can you say, and this isn't specifically to a specific speaker, what can you say about the composition of the organics that were found close to the leopard spot? Are they PAHs like in the Cordier measurements that Teresa discussed, or some different aromatic bearing phase? So I don't know, Joel or Mike, if you want to jump in there. You have 1 minute.
I can describe them as macromolecular organic carbon. That is the identification that has been made by the Sherlock team. They possess a Raman G band. I don't know that I can speak to it in any more specifically than that, but I would direct you to Ashley Murphy's talk on Friday, I believe, where she'll be getting into the details of the Sherlock detections in those deposits.
All right. Thank you. And let's thank our speakers for this portion of our session once again. All right. We are still just getting started. Mars is great. Mars is awesome. We're going to shift over to a few other ocean worlds as well, given that this is a joint session. So our next speaker is Catherine Zarilla, and she's going to be talking about potential phosphorus redox chemistry on Enceladus.
All right, good morning, everyone. I'm really excited to talk to you guys about some of the work I'm doing as a postdoc at JPL in the Origins Habitability Lab, specifically focusing on redox reactions involving phosphorus. If they can, there it goes. So we've talked a lot about phosphorus this morning and how it fits into geological context. And so I'm excited to help shift the conversation to think about how phosphorus can be incorporated into different prebiotic and biological reactions. So when we're thinking about biology and prebiotic reactions, one of the tools that we have to think about these types of reactions is the CHOMPS elements. So that'd be carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphorus. So as life has evolved on Earth, these are the elements that facilitate prebiotic and biotic reactions as we understand it. And they're necessary for biology to function on Earth. Out of these elements, phosphorus is considered a limiting element. And this is not just because of its geological context, but also because of its incorporation into prebiotic and biotic reactions. Phosphorus plays a vital role in biology as we understand it in lots of different forms. For example, the backbone of RNA and DNA, as forming the charged head of phospholipids and bilipid membranes, and the energy currency for the phosphorylation reaction of ADP to ATP. So historically on Enceladus, it has been thought that the CHOMPS elements, many of them were present within the subsurface ocean. Until recently, phosphorus was also considered a limiting element for the potential habitability of Enceladus. But with this recent discovery, this has opened up a whole new range of potential prebiotic reactions that could be occurring within the subsurface ocean. If phosphorus is present and participating in these prebiotic reactions, understanding these specific redox reactions that could be participating in is really important to understand the potential habitability of the subsurface ocean. However, not all phosphorus species are going to be created equal. When we're thinking about phosphorus incorporation into life, it's really important to think about the specific type of phosphorus species that we are narrowing in on. So the specific type of phosphorus species that was detected by Cassini is phosphate. And this is going to be in the range of about millimole scale. And other phosphorus species might have been detected, specifically the more reduced form of phosphorus, phosphite. However, that's going to be in a lot lower concentrations. So putting it in the context of an origin of life perspective, looking at a redox reaction of phosphite to phosphate is really important. In the origin of life on Earth, phosphorus is also considered a limiting element, as phosphate is essential for biological reactions to function as we understand them. However, it's not really going to be present in the early Earth environment. So origin of life scientists will commonly look at more reduced phosphorus species to kind of fill that role and see if it could be undergo a redox reaction to create the phosphate. So understanding any potential periodic reactions involving a redox of phosphite to phosphate is really important to constraining any type of phosphorus periodic reaction that could be occurring. So as I just mentioned, phosphorus and its influence on the limitation in prebiotic reactions is really important when we're thinking about the origin of life on Earth. And this is because phosphate is the specific type of phosphorus species that's necessary for biological reactions to function. Phosphate has a lot of really unique structural attributes that really cannot be replaced by a more reduced form of phosphorus species. However, the issue is that phosphate is one of those phosphorus species that's going to be sequestered into minerals really easily. So this has led to a common problem in the origin of life community known as the phosphate problem, where the necessity of phosphate is really important for our biology to evolve as we understand it. However, it's not going to be readily available and soluble to participate in prebiotic reactions. So again, one of the solutions to this phosphate problem that has been postulated is a redox reaction of a more reduced phosphorus species to a more oxidized phosphorus species. So shifting to talk about where these redox reactions would be occurring, Enceladus is proposed to have a hydrothermal systems on its seafloor. And from an origin of life perspective, these are really important as it's one of the locations thought to be an origin of life. Within these systems, various different minerals are thought to be present. And this is really important when we're thinking about those prebiotic reactions, as prebiotic reactions are thought to have been catalyzed by divalent metal cations instead of protein catalyzed biological reactions that we would see later in life's evolution. And so what we're really looking at here is we're looking to see if a redox reaction of phosphite to phosphate could be facilitated by some of those minerals that we would expect to see within hydrothermal systems. And understanding that redox reaction can help constrain any potential prebiotic chemistry that could be occurring within these hydrothermal systems. So to do this, we conducted a laboratory experiment with conditions that would be important for understanding redox reactions. So we replicated these conditions through benchtop experiments, specifically selecting iron and phosphorus species that would be important to those redox reactions. We created a solution that was alkaline around pH 9, anoxic. As we're looking at a redox reaction, we want to limit the amount of oxygen that would be contaminating the sample. And we also created a saline solution that is carbonated and saline in order to replicate the soda ocean that we expect to be on Enceladus. So with these experiments, we created these solutions and titrated them to pH 9. We added carbonate and salt as sodium carbonate and sodium chloride. We then added a phosphite salt in 3 different concentrations, 5 millimoles, 25 millimoles, and 0.3 molar solutions. Now, those concentrations are not going to be a one-to-one comparison to Enceladus. What we really were trying to do is try to amplify the signal from any reactions that would be occurring within the solutions. We then added ferric chloride as the iron 3 source, again, in 3 different concentrations, 0.03 molar, 0.15 molar, and 0.3 molar. Again, not trying to completely replicate an Enceladus environment, but really try to amplify the signals from any reactions. We then left these to react in a nitrogen-filled glove box to create an anoxic environment. And then the solutions were allowed to react for a 12-day period, with sampling occurring at 0, 3, 6, 9, and 12 days. So basically what we did is we took the supernatant 2 milliliters of it and then analyzed that with 31P NMR in order to determine the specific type of phosphorus species that would be present in those solutions. So we chose 31P NMR in order to specifically identify the phosphorus species. And this is a really common approach taken in the origin of life, as this 31P NMR is able to very accurately detect the specific type of phosphorus species and identify it as opposed to all the other phosphorus species that would be present in the liquid solution. So in the controls we did, we found that phosphite was identified by 2 peaks, one at 4.7 and one at 1.18. And phosphate was identified with a singular peak at 2.81. And over a 12-day period, we found these would be stable, indicating that within this saline carbonated solution, they were not going to experience any type of degradation or redox reactions. So going into the results, in our lowest phosphite concentration, 5 millimoles, and our lowest iron concentration, 0.03 molar, we did not see any redox reactions occurring even before the addition of iron. Over a 12-day period, we did not see any changes, indicating that no phosphate was being produced at detectable levels by this method. If we increase that phosphite concentration, so we bump it up to 25 millimoles, but we keep the iron the same, we are not seeing any redox reactions. Before the addition of iron, we do see a little peak that could be indicating phosphate. However, that is associated with the reagent and was able to be reproduced in just water. So again, we did not see any changes over a 12-day period, and phosphite was observed at every time point. So what does this tell us? This tells us that the redox reaction of phosphite to phosphate is probably not going to be occurring in the same way as we think about it in the origin of life, especially not with the iron 3 oxidant. We replicated these experiments in hydrothermally relevant temperatures at 70 C, and we still did not see any type of redox reaction. It was consistent with our previous results. If similar chemistry is occurring within the hydrothermal systems on Enceladus, that means that we need to be looking at different types of oxidants that could be facilitating a redox reaction of phosphite to phosphate. So in summary, we did not see a redox reaction of phosphite to phosphate occurring within these solutions, at least not detectable with our analytical method. Therefore, phosphite might not be a major contributor to the overall phosphate inventory that we are currently seeing in the Enceladus subsurface ocean. If we're really wanting to constrain the potential influence that phosphorus would have on prebiotic chemistry on Enceladus, it would be really important to look at other types of oxidants, taking a cue from the origin of life community, that could be facilitating these types of redox reactions that would be necessary for life to emerge as we understand it. So I'd like to thank the Origins Habitability Lab for helping support this work. They're all amazing, and I will go ahead and leave it on my summary slide. Thank you so much.
Thank you. And next up, we have Bapia Peitzer, who's going to be discussing development of spatially offset Raman spectroscopy that could be used on Europa to detect astrobiologically significant molecules.
Good morning. Thank you for the introduction. First, I would like to acknowledge Brandon, who's a graduate student in my group that's done all of the work I'm going to talk to you about today. So like everybody here, we're interested in figuring out if there's life in space. And the speakers before me have covered, what are the key things that we need to look for to indicate that there is life in space, including water and energy. Our target is looking at Europa, which is the fourth largest moon of Jupiter. It has this icy crust, and it's known to have a subsurface saltwater ocean. And then the presence of these different molecules have already been demonstrated through things like the near-infrared mapping spectrometer, the Webb telescope. And so there's pieces indicating that there could be life on Europa. And so the question is, how do we find it, particularly with this icy shell? So what our aim is to develop new methods for highly specific detection of organic and inorganic material on Europa. And our area of expertise is Raman spectroscopy. And I'm going to talk to you a bit about a new way that we're trying to do particularly subsurface measurements. With the proposed Europa lander, NASA said that they want to go down at least 10 centimeters below the icy surface. So can we do that? What we're proposing is to do it without having to drill holes to get there. Oh, could you click below those three things? They move, the GIFs. No, sorry. They have little buttons, even if you can't. So Raman spectroscopy is a vibrational spectroscopy. If these would move, oh yeah, there you go. Each of these vibrations is present in our Raman spectrum as a peak, so we can very specifically identify. Yeah, that's my favorite one, the WAG. So we can very specifically identify peaks in our spectra correlated with these different vibrations. And what's key about Raman spectroscopy is that if we changed, for example, this thiol group to something else, our spectrum would change. So Raman spectra are considered to be molecular fingerprints. A type of Raman spectroscopy that most people are not familiar with is called spatially offset Raman spectroscopy, or SORS. This is a method that was developed to look at multi-layered samples. Originally to look at things like chemicals in packages or bottles, so that you wouldn't have to open something to look at what was inside of it. It was then moved towards biological applications, primarily disease diagnostics. So people have applied it to looking at bone disease, so measuring bone spectra through the skin, looking at glioblastoma in small animal models. And then our group has worked on neurochemical detection through the skull to see, without having to drill holes, can we detect neurochemicals? So the way that SORS works is you have your multi-layered sample, you have your laser incident on the surface, and the light that's scattered from the top layer travels back along the same trajectory as the incident light. The photons can travel into the lower layer, they migrate laterally, and then they scatter back out. So the idea is if you collect your Raman scattering here at some distance that's spatially offset from your incident light, you get information about this lower layer. There's two geometries that you can do this in: a point collection where you illuminate and then move your collection optics to create the offset, or the one that I'm going to tell you about, which is called inverse SORS. This is where you use an Axicon lens that turns a laser spot into a ring of light. So then you collect your Raman spectra from the center, and your offset is created by the radius. This is key because this spatial offset is correlated with the depth that you're measuring at. So it's a good way to say how deep are you going. This is our system. We use a 488 nanometer laser. We send the light to a sample, goes through the Axicon, it's backscattered and detected with a detector and a camera. This is just what it looks like on a laser table. So one of the speakers earlier this morning talked about biosignatures and how it's not just looking for microbial life, but also things like minerals. So we started with looking at sulfate mineral mixtures and ice. So here are the Raman spectra. These are just normal Raman spectra of sulfate hydrates. So we have gypsum and epsomite, and you can see that the two dominant peaks are here at 988 and 1012, and these arise from the SO4 symmetric stretch. So those are going to be the key things that we're going to look for. What we did is we took the two minerals, we kind of ground them up, and then made a stack sample. So in the bottom layer is the mixture of gypsum and essonite. We added water to freeze it. Then we added a layer of ice on top of that. We put in a layer that is PTFE or Teflon. And then we put we froze another ice layer on top. So this entire thing's about 3 centimeters tall. The top layers are 2.6 centimeters and our mineral layer is 0.6. On the left, you have the Raman spectra. So these are the concentrations of the two minerals. Everything highlighted with T is from the Teflon. And so you can see the Teflon really dominates our spectra. But here we have the two at 989 and 1014. We have the two vibrational modes from the mineral mixtures. So we were able to detect both gypsum and epsomite at a depth of 2.6 centimeters. The other thing that we are interested in looking at is amino acids, because on Earth, they're the building blocks of life. So can we also find these in space, and would we be able to detect them through ice? So we have here the normal Raman spectra of first the solid of tyrosine with the vibrational modes listed here. And then we have a solution that's 2.2 millimolar. You can see that we lose a lot of the vibrational modes when we put the tyrosine into water. But we do have two key modes. This one is from the CN stretch here, and the 1280 mode is this OH stretch on the ring. So we made a similar sandwich. Again, this time we have ice at the bottom. We put tyrosine in the middle between another ice layer, and then we put our mineral mixture at the top. And so here we did this at 2 different concentrations. Oh, these are, there used to be pictures here. Okay, we'll go with the top ones. At least there's some. So we have here on the top is the spectrum of the surface. So what you see is the modes from the epsomite and the gypsum. So we're just measuring at this top layer right here. In the purple, what we've done is gone to a depth. So we used an offset that's about 3 centimeters. And this is at 57 micromolar. So this is about 10 parts per million. And we were able to see both. You see the epsomite and the gypsum again, because we're going through it and coming back out for the backscatter. So we're going to get contributions from those as well. But we do have the 1150 and the 1280 peaks from the tyrosine. If you could see these two down here, these were done at 471 nanomolar. So this is about 85 parts per billion. Really what we want to get down to is 20 parts per billion, but we're working our way there. And what you would see is those two peaks are also there, along with the epsom and gypsumite on this side as well. And this was detected at a depth of 0.6 centimeters, so not quite as deep, but we also went to a much lower concentration. I think I talked really fast. So what we've been able to show is we can do this in mineral mixtures. We can get going through Teflon, so through a plastic layer, and still measure the mineral mixture at 2.6 centimeters of depth. We're able to do the tyrosine at 2 different concentrations, which are getting close to what we think we should be able to detect on Europa. And we're developing new instrumentation for this. And we're going to continue to push these forward to try to reach those limits of detection that are relevant to Europa. But we're making our way there, and we're making pretty good progress, I think. This is our group. And again, Brandon is the student right here that did all of this work. And I talked really fast, so thank you.
All right. Our next speaker is Lily Clow, and she's going to be telling us about how machines are going to take over the world. No, she's going to be talking about machine learning based tools and diagnostics for interpretation and detection of biosignatures on ocean worlds.
Thank you. Okay. All right. Hi, everybody. My name is Lily Clough. I'm a graduate student at the University of Tulsa and part-time contractor with Aurora Engineering at Goddard, so my life is really busy. I'm here to talk to you about explainable machine learning in false prediction diagnostics for ocean world biosignature applications. And I'd like to acknowledge my esteemed colleagues, Bethany Teeling at NASA Goddard, whose data we use to develop and validate this tool, and Brett McKinney at the University of Tulsa, who's with me here today. And this is our first LPSC, so we're really excited. Okay, so we are looking for biosignatures in ocean world analog isotope ratio mass spectrometry data. Bethany's data set is made out of abiotic and biotic brines, pH values acidic to alkaline, ionic strengths 0 to gooey, like 13, so very slimy. And so we have different salt components, and we're measuring volatile CO2 in the headspace evolved from these brines. The water is an exaggeration. We actually use 0.5 milliliters in these 12 milliliter vials, so it's just for illustration. Our data set, after we do processing, quality control, we calculate some variables. We have 104 features. Using our feature selection algorithm that I'll talk about more, we reduce that space to 5 predictor variables for machine learning. So that's on the scale that's human understandable. So our sample size is also small by machine learning standards. So we have 174 samples. It's also imbalanced, which can be challenging. This data set's also very complex and high dimensional. This paper came out yesterday, my first author paper. Yeah, and so this is a main result from this paper. This is a slightly different split than is published in the paper, but we get around 91% training and test accuracy on this data. What we're particularly interested in our next project here is the false positives and false negatives for biosignatures. So we have 2 false negatives, which are biotic samples that are incorrectly predicted to be abiotic, which would be a tragedy in a space mission. And then we also have 1 false positive, and that's an abiotic sample predicted to be biotic, which is not good for your career, maybe. And so we would like to avoid those things. We would like to prevent an erroneous report of a biosignature or an erroneous report of no biosignature. And so how can we do that? We are building on a tool that was developed by Brett McKinney's lab previously at the University of Tulsa for bioinformatics applications. This is a feature selection tool, so it identifies important predictors in machine learning models. It identifies main effects for variables, so think violin plots that are going to separate out the means, and statistical interactions, which are a conditional correlation based on class. So it's a differential correlation. So in this plot, we have X and O samples, so 2 different classes, and a 2-dimensional variable space. And the linear correlation for the O samples differs than the linear correlation for the X samples. And we see this in Bethany's isotope ratio data. Our paper, we selected these 6 predictors for biosignatures, and this is a regression association interaction network. And so this helps us visualize how the variables we selected work together to affect model predictions. The magnitude of the nodes here are the main effects that the variable has. And the edges are the interaction effect and direction of prediction. And so this helps us see how these variables add up together to affect model outcomes. So our global MPDR feature selection calculates feature importance by regressing over sample pairs using projected distances, which I'll illustrate in the next slide. This takes advantage of high dimensional data to detect interactions. You may have heard of the curse of dimensionality. Brett and one of his colleagues like to call this the blessing of dimensionality. And so we can find interactions. We also employ a penalized regression. Local MPDR, in contrast, calculates feature importance for a single sample. So global MPDR, we use all the training data. We find features that are globally important. Local MPDR, we're looking at one sample to diagnose if it's a false prediction. We expect that local scores of important variables are lower for false predictions than true predictions by the way that the regression works. Okay, so here, this is kind of a toy 2D example of how this works. So we have sample 1 is actually of class X, and it's been correctly predicted to be in class X. Has a neighbor X2. See if I can. Yes. Okay. So 2 neighbors, X2 in sample 3 here. Sample 3 is of a different class, and the projected distance on this axis for important variable A, which discriminates against the X's and O's, is smaller for the sample that's of the same class than for the sample that's of different class. And this is key for us identifying false predictions. And so that means that this delta H, this we call it delta hit, is going to be small, and we assign an indicator variable delta value 0. Delta miss is large. We assign an indicator variable delta 1. And then we get scores that look like this. So the green bar is variable A, a 0 value. The local score for sample 1 is positive and agrees with the global score for this variable. And so that would be an indication that this is a true prediction. In contrast, imagine if sample 0 or sample O was, or sample 1, excuse me, was misclassified to be class O. And then the sample nearest to it, X, is no longer a hit, and it's a miss. And now delta miss is smaller than delta hit. And that's kind of flipped what is indicating variable importance for us. And so in this case, variable A is no longer important for discriminating X's and O's. But that's in contradiction to the global variable important, which the global over all samples does discriminate. And so this is a negative local score, and we have a false prediction. So I'm going to show you guys some results on Bethany's real biosignature data. Okay, so this first one is a true positive, so real biosignature correctly predicted. The local scores here show blue positive importance scores. These features are ranked in order of global importance. So the top feature has a large magnitude blue bar. This adds up to a positive local score. Additionally, the random forest classifier reports a high probability for biotic. And so we can feel comfortable that this is probably a good prediction. In contrast, this is a false positive. In the top 2 global NPDR variables are negative, have negative scores here. And that adds up to a negative total local score. Additionally, the random forest classifier has a biotic prediction of only 55.5%. It's not sure. The next time you run it through, it could assign it abiotic. And so we would flag this as a potentially false or problematic prediction. We tested this on simulated data. And so I forgot to mention that we use this on test data. So we train the algorithms on training data. These results are test data. Classifier hasn't seen them before. Global MPDR hasn't seen them before. And as you can see, the p-value for both simulated data sets is extremely small. One data set we made with 300 samples. So there's a tool in the MPDR R library to make realistic simulated data with the correlation structure, with main effects, with interaction effects. You can control the sample size. And so it's great if you have tabular data and you would like to simulate it. And so you can see that we have significant p-values for both of these simulated data sets. Okay, in summary, we can improve interpretability and trust in machine learning biosignature models. My paper is all about interpretable models. It's important that you use a model that's appropriate for your data. And so we found that we can distinguish between true and false predictions. We found that the scores are statistically significant. Additionally, you can interpret why a sample was predicted to be in a certain class, like using that regression association network along with the local importance scores. Other local importance methods do this. Random Forest has one, and there's one called LIME. They both, however, cannot take into account statistical interactions. And that's important in complicated realistic data sets because Bethany's data has very few main effects to distinguish biotic and abiotic, which we show in that paper. Okay, I would like to acknowledge Steve Bates at NASA for incredible laboratory work, and this is my paper. You can email me at lily.a.cluff@gmail.com.
Thanks. And now we'll move on to our last speaker of the session. So we have Michael Way, who's going to be discussing what the end Permian can tell us about deep time future Earth in the context of exoplanetary studies.
Great. Hope you all can hear me.
Yes, you sound fine. Go ahead.
Awesome. Okay, great. Thank you for reading out my title for me, so I won't do it again. This is some work I've been doing with colleagues here in the United States and also in various European departments, as you can see. Next slide, please. So first I want to just cover the end Permian. I think most of you probably know what that was. This is a time period where one of the major great extinction events in Earth's history took place. I'm going to model the period just before the extinction event itself. But at this time period, Earth was in a supercontinent state, as you can see, and I just put up a map on the left of what that looked like in comparison to modern day. Day length was about 30 minutes shorter back then, and the amount of sunlight we received was about 3% less than we receive today. Next slide, please. The other period I'm going to talk about in addition to modern day is about 250 million years in the future, and we've done some geodynamical modeling work that show that Earth will be in one of two possible supercontinent states. One is a low-latitude supercontinent we call Aurica, and the other is a high-latitude supercontinent called Amasya. Next slide, please. So hopefully if you hit the next slide, we'll see how Amasya is formed. Is that working? Yes, this is done by Hannah Davies, one of our collaborators. And you can see how everything kind of comes together. You've probably seen the ones for past Earth, but this is possible for future Earth. Next slide, please. So at this time, we were, as I say, it's a supercontinent state, low latitude. Insolation is about 2% more than a day. Length of day is about 30 minutes longer than today. Sorry for the typo. Earth is spinning down, not up. Next slide, please. An upfront confession. Of course, the parameter space this far into the future is vast, but we have to start somewhere. So I'm going to go through a few different things here. Next slide. So the CO2 budget, of course, is unknown. There are no IPCC projections this far into the future, so we're just going to go with pre-industrial, and I'll give some justification for that. Next slide. Earth history suggests that 285, which is 1850 pre-industrial, is not an unreasonable value, and I show here a plot on the lower right from Jeddah in 2024. It's a little on the low side, but again, not unreasonable. Next slide, please. Okay, how about probability of a mass extinction event for lip volcanism in the next 250 million years, the kind of volcanism that caused the end Permian, which gives us modern-day Siberian traps. Next slide, please. I would say it's very high. This is a paper I wrote with Richard Ernst and Jeffrey Scargill. Richard is an expert in documenting lips, and Jeffrey is an expert in time series analysis. And if you go to the next slide, we'll see that there's about a lip every 10 million years in Earth history on average. Why is this seldom mentioned in future Earth science fiction scenarios? Next slide. Because it's too boring, of course. Next slide. What about the carbonate silicate cycle? This is often stressed a lot in studies of exoplanetary systems and how important it is. But I think we should always remember that in the past 4 billion years, Earth's kept basically the same global mean surface temperature to within a factor of 2. If you go to the next slide, you'll see slide again from Judd et al. 2024, covering the entire Phanerozoic, and you can see exactly what I'm talking about here. Global mean surface temperature on the upper scale is showing not that much variation. Okay, there are periods where we had snowball states or slush ball states, however you feel about that. But otherwise, the surface temperature for Earth for most of its history has remained fairly constant, even though we know that a tectonic state was different, and certainly modern day subductive plate tectonics with carbonate silicate cycle did not exist 4 billion years ago. Next slide, please. So what about CO2? What happens? So what we think is going to happen is that as we go to higher insolations, the sun gets brighter, we're going to end up with lower CO2 amounts. That's going to make our plants unhappy, and that's going to produce less oxygen. If you look at papers from Ozaki and Reinhardt I cite here, and a more recent paper by Graham and Ozaki and Reinhardt, they say in a gigayear there'll be no land plants left. And in Graham, he's a little more optimistic, using a little bit different modeling efforts, showing in 1.8 gigayears there's no land plants. Next slide, please. This is the plot from Ozaki and Reinhardt, and you can see where 285 is on the plot in the middle one. I know it's hard to see this, it's not so important, but you can see that in one limit, the plants can't survive beyond 150 ppm, and another limit, it's down to 10 ppm. Next slide, please. So we've done a few experiments with these different scenarios using the Rocky 3D general circulation model. That's our climate model that we use here in New York City for these 3 different time periods. Again, the N-Permian I discussed, modern 1850, and Aurica. So if we go to the next slide, you can see some of those results, hopefully. Yes. And I think what's interesting here is you can see on the left, I'm showing you the N-Permian with a slightly lower insolation, but with a slightly higher CO2 value. So again, this is just before the main extinction event, and the proxies and modeling efforts have shown that you could have CO2 ppm around 900. On the right, we use the Aurica simulation, where again, the insolation is about 2% higher, and the CO2 amount's just modern day. And these climates, I mean, this is very qualitative for the audience here, we don't have time to go into details, are looking actually more similar to each other than even modern day Earth, where you can see the poles are much colder on modern day Earth than they are in these other 2 scenarios. Next slide, please. This is what precipitation looks like. Again, I would say that all 3 don't look that different, but we think that the N-Permian and Aurica are a bit more similar. Next slide, please. Okay, so what can these tell us about deep time future? Let's go to the next slide. So what I'm going to do for the exoplanet audience is I'm going to move our system to the distance of the TRAPPIST-1 system, about 40 light years away. I'm going to show you some transmission spectroscopy of these 3 simulations using the JWST near spec imaging camera, or a spectrograph, excuse me. Next slide, please. And what we see here, I'm sorry I didn't have this a bit better annotated, is the contrast in parts per million between the star and our planet at the TRAPPIST-1 distance. And I think what you see most obviously is that the spectra are not that different. Here we see the N-Permian in blue is a bit higher in terms of how much contrast there is, and that's mostly because these big 3 features you see here are CO2 features, and of course the N-Permian has about 900 ppm CO2 as compared to the other simulations were only at 285. The smaller features at 2 micron and about 3.3 micron, I'm sorry, not 2 micron, at 1.5 micron and about 3.3 micron are the CH4 features, which you don't see huge amounts of differences in. Okay, next slide, please. Finish a little early here. So what I want to point out here is that it looks like Earth in these simulations is indistinguishable from minus 250 million years to about 250 million years into the future. We really can't distinguish these climate scenarios from each other. And we have another project we're doing the same throughout the entire Phanerozoic. So we'll go back 500 million years into the past. So another 250 million than we've already gone. And we're already starting to see that, again, those things don't change so much. So the take-home message here is that it's very hard to distinguish Earth's climate in a transmission spectrum at the distance of TRAPPIST-1, even though we see great changes in CO2, continental layout, albedo, precipitation, and all these different things. So thank you very much for your time.
All right. Thank you, Michael. We're now entering into our final Q&A period. So I'd love to invite our last 3 in-person speakers back up to the stage. And Michael, please do stay online. boy, in a mere 2.5 hours, we have gone from potential biosignatures on Mars and ancient ocean world to exploring biosignatures on current ocean worlds and how the machines are going to take over, and then a quick whirlwind tour of the past, present, and future of the Earth in comparison to exoplanets. So I don't think we've left much out. But please do come to the mic again, name and affiliation, please. I don't see a lot of online questions, so we'll take ones in the room until we start to see some online. So go ahead, please.
Hi, David Bracey from University of Florida. All great presentation, thanks. I have one question for the three first speakers, so I will try just the first one. So for your phosphate production, on origin of the life, when we do some experiments, most of the time the kinetics is faster when you have a substrate, and oftentimes when the phosphate creates, it directly connect and bond with the organics. So did you try, or before like switching for other oxidants, do you try some substrate with this water phase, and maybe after adding some organics to make some complexes and stabilize everything?
Excellent question. So that is something that we're thinking about, but unfortunately, this was more preliminary. We were trying to observe if the redox reaction could even occur, and it could be supporting the phosphate inventory. As phosphate was detected as its own anion, we wanted to kind of limit it and go for really baseline. So we didn't do that, but I would love to talk to you afterwards about it.
Great. Yeah, great talks all around. I'm Joey Pasterski at NASA Goddard. My question is just go in order to Lily. First off, congrats on publication. That's what timing. But I was curious, because you had such a small data set to work with, 174 is extremely small, as you know. And I was curious if you had to do any kind of like outlier removal, or if that could have played into your false positive, false negative situation.
Yeah, that's a great question. It's nice to see you.
You too.
Yeah, so our sample size is small. We did quality analysis, quality control, and we removed like some problematic samples that had like atmospheric leak and things like that. So yes, that is really important. We did not specifically like remove outliers after that. And so yes, I do think that some of those false predictions could be, if not like strict statistical outliers, like maybe isolation forest or something like that, would label them as outliers. And yes, that's definitely something that like we have some undergrads like working on and stuff like that.
Awesome. Great job.
Hi there, David Burt, also NASA Goddard. I also have a question for Lily. This is fabulous work, and you won't hear me complaining that you started with isotopes because they're the best. But I was curious, do you guys have any plans to either expand the sample set that you're looking at, like looking for different biomarkers or biomarkers in different settings, or to expand your study to include different measurement techniques?
Yeah, thank you for that question. It's nice to see you too. Yes, so we were awarded a NASA EPSCoR grant in Oklahoma at the University of Tulsa, and we are working with Bethany to perform experiments to gather more data. We would like to add to our sample size. So these experiments were done at Earth temperature and pressure, STP. And so our funding is to do cold temperature, hot temperature, higher pressure, lower pressure experiments. And so we would absolutely love to add to this database and make it more agnostic to like environmental conditions.
Fantastic. Thank you.
Hi, this is Xiaowei Wang from Cornell University. I have a question for first speaker, Zuria. So the first question is, did you see precipitation in your experiment system?
Yes, that's an excellent question. So as lots of previous work has shown, these types of experiments do precipitate a mineral. And so when we did add specifically the iron, before we added any of the phosphorus, no precipitate was formed. But with the addition of the ferric chloride, we did see a precipitate start to form and settle on the bottom. We did not analyze, I didn't present any of the data from the mineral analysis here. We did run FTIR on it, but because the experiment we were running was specifically trying to look at the dissolved phosphorus species, as that is what would be most prebiotically relevant, and it was what was detected by Cassini. We didn't focus on the mineral.
Yeah, so and there could be a reason that you did not see phosphate because at the pH in your experiments about pH 9, right?
Mhm.
So on this pH, iron will precipitate as like iron hydroxide and also iron phosphate. Iron phosphate is also a precipitate.
Yeah.
So there could be a possibility that even if they're phosphate form, it can like combine with iron 3 to make precipitate so that you cannot detect it in the solution. So there's a possibility.
Yeah, so that was actually one of the things that we were trying to also observe in this experiment. So if the redox reaction was progressing and the phosphate was being produced, then we have a whole new reaction we're looking at, right? Then we're looking at the competitive binding preferences of the iron to either the carbonates or to the phosphates. And based on previous work like HAL 2022, they found that within these high carbonate solutions, the iron's going to preferentially bind to the carbonates instead of the iron. And so that's why we were kind of looking to see if we could replicate this with iron 3, associating the redox reaction with phosphite with it.
Okay, yeah. Just one last thing. There's just another like possibility that because iron hydroxide can also absorb phosphate because they have positive charge at the surface. So this can also be an explanation for why you don't see phosphate in the solution.
It's definitely possible.
Great.
Hi, I'm Tim McCoy from the Smithsonian, and I want to say to the third speaker, I went to my first LPSC in 1988, and I'm a civil servant for the U.S. government. With everything hanging over us, it's enriching to see someone so enthusiastic about coming to this meeting, and congratulations. But my questions for the first speaker, I guess I'm not surprised you don't see this reaction. I'm not sure you actually need this reaction. A group of us on the OSIRIS-REx team just published a paper in Nature reporting an entire evaporite sequence from the Bennu samples. And yeah, the phosphate will come out of solution if there's calcium in there. But if you have a high carbonate concentration and you precipitate calcium carbonates, calcite, and dolomite, you can keep it in there. And we see this in magnesium, sodium phosphates that stay in there. So the fact that you have a sodium and carbonate rich system and you need phosphate in there, I guess I'm not sure you really need phosphite to phosphate precipitation. It may have been there since 4.5 billion years ago. But in the same rocks, we also see not phosphite, but phosphide. So we see iron chromium phosphide, andreabibonite. We see alabogdanite, which is iron nickel phosphide, and commonly schreibersite, which is iron nickel phosphide. And so I wonder if you've given any thought to phosphide to phosphate oxidation in these to enrich the amount of phosphate available for these reactions.
Yeah, that's an excellent question. We were focusing on the phosphorus species that was previously published to be the most detectable. It's definitely something that I'm interested in, but it wasn't a part of this study.
Hi, Marshall Seaton, JPL. I have a question for the first speaker. So I'm not sure if you had a chance yet to examine the degree to which those reactions are dependent on pH. I know that 9's obviously a great starting point, for Enceladus, but there's some also work that suggests that the pH could be significantly higher than that. And I was just curious if you thought about that.
Yes, that's a great question. So we did choose pH 9, as you mentioned, because it was the most relevant to Enceladus. We did not, I did do some experiments that were untitrated, and that pH was a little bit higher, around 11. And we still saw similar chemistry.
Well, hold on, we've got an online question if we could. Go ahead, Denise.
Thanks. So this is from anonymous attendee. We have a question for Dr. Wei. Why did you specifically choose plus or minus 250 million years? If you would have chosen Archean, how do you think the transmission spectroscopy would have behaved? And I see that you did answer it online, but if you could share the answer for the rest of the people in the room.
Sure, I'll just read what I wrote. I chose those particular scenarios because I had them as part of other projects, as we often do when we do modeling studies. We have a lot of models. But I do have some Archean models that show that they are a bit more different from these, but mostly because of changes in CO2 partial pressure, which we assume there was more CO2 back in the Archean to keep the planet temperate. Thank you.
Hi, Mendy Uzalu, private citizen. This question goes, I think, to Lily. Super. So first of all, I was excited to see some machine learning creeping into some of our science here. So I had a couple of questions. So I understand why you would choose an explainable model to begin with, but one of the, as you well know, the true power comes when you can increase the size of the model, it becomes less explainable. So the question is this: how did you figure out what those 5 parameters were? And specifically, how did you determine how decorrelated they were from each other to make sure that you did not introduce bias? And then the second part of the question is, how do you think your model would predict if you increase the number of non-correlated inputs, but the model became less explainable?
Yeah, thank you so much for that question. The paper that we published explains this in a lot more detail, but the reason we chose an explainable model is because we are looking to predict biosignatures. And we do not want to leave that up to a neural network. So I think it's nice that we have machine learning and AI creeping into science, but I also think we need to make sure that the models are not just overfit. So like the larger the model, the more parameters that you introduce, the more likely it is that you're going to overfit. And we use random forest because as you increase the number of trees, it's not going to overfit. And then what was the second part again?
Oh, you know, what do you think the results would have been had you gone to a less explainable model?
Yeah, so
and I have a quick follow-up
Sure.
too, if that's okay.
Okay, so in our paper, we compare the 5 predictors. So we chose the 5 predictors using global NPDR. So we have an R library for that. We used the training data. We regressed on the pairs of samples, and the coefficients from that regression are the variable importance scores. And so out of our 104 predictors, NPDR reports based, depending on the training test split, 5 or 6 variables that are important for biosignatures. And so we take all of those and we put those into a new random forest classifier it's faster, it's more interpretable. And we've had undergraduates look at neural networks for this data. They do not do better. In fact, they do significantly worse than random forest. And it could be because of our small sample size. So I will say that like we would need thousands and thousands of samples, which in isotope geochemistry, that is a significant lift. So, and so we use random forest again for that reason, because we have a small sample size.
Yeah, okay. And that last comment you made, I think, helps explain where I wasn't kind of catching on, that this data is hard to get. But I'll just leave you with one very quick thought. I mean, this kind of machine learning is being used in very high stakes processes like, breast cancer detection, for example, where false positives and false negatives carry their own problematic. So overfitting, if you are able to get more data, that overfitting will be less of an issue. And don't just stick to random forest, potentially.
Thank you.
I will continue on the second speaker for the Raman. On the surface of Europa with the radiolysis, we will have from all radiations and even X-ray on deeper surfaces, we will have degradation of organics within the ice. So how deep can you expect the Raman to observe biosignatures, reflection observations with Europa lander?
So I think the question is, how deep do we think we can go?
Yeah, with your technique.
Okay, so far we've done up to 3 centimeters. We have done in other systems, so we've gotten to 60 centimeters in other systems that are not ice, that are human or like biological tissue type systems. We've gone through bone and gone to 40 millimeters, so 4 centimeters through bone. So we've done various complex materials and gotten to depths that we think we can. We haven't gotten to 10 yet in any system that we've done, but we've definitely gotten to 6 centimeters. So we're getting close to where we need to go. I think it's just we just need to work a little on optimizing our system for what we're trying to do here.
Yeah, Great, thanks.
Mhm.
And question for Lily. On your 82% of the high score on like the best biosignature you had, what is the score you want to reach? Because in biology studies, we like between 95 and 99%. How, like, when we were gonna have data from Enceladus or Europa, what level do you trust?
Okay, that's a good question. So that probability is not a confidence interval. It's the random forest like reported probability that this is the class. And so we rarely get things like 95 and 99%. And so anything I think mid 70s and upper is pretty good. But when it's like close to like 60, 50%, that's when we're like, if we give this to the model again, it because of like stochastically how things work, like maybe it'll come up with a different class. And so, but when you have those higher probabilities, when you run it through like a model, it'll consistently. So it's like, how sure is the model? And we would like to, we do like to see those 80%, and it's great when we have those 90%. We see that sometimes.
All right, I'm going to take chair's prerogative and ask a question for Bhavya. So you talked a lot about Raman. Of course, it gives us the chemical composition, but also gives us some diagnostics on the chemical environment. And we've noted that, epsomite, magnesium sulfate, you can detect, different hydration states, and even if it's a vitreous glass. And so I'm curious, when you talked about freezing your samples, can you talk a little bit more about sort of those conditions, how quickly you froze them? Do you expect, different hydration states or glass or things like that?
Sure. So for this sort of first try at this, we just froze them in a regular freezer. So our next step is we're going to try to flash freeze things to get a better system. One of the things we are doing is, and I didn't have time to show it, but we're monitoring the OH vibrations. And so looking at how do those change under the different conditions. So that is also something that we're looking at to monitor hydration.
Hi, Bumsu Kim from NASA Johnson Space Center. First of all, thank you all for the great talk. I have a quick question for the fourth speaker. So I'm an organic geochemist studying astrobiology, but actually my background is paleoceanography. So it's really great to see paleo modeling and future projections. But one question is the Permian-Triassic boundary was one of the key extinction event that caused a change in habitability, right? But also there were a lot of, carbon cycling perturbations in the marine that a lot of paleo people think that caused, so like hydrate dissociations or other volcanism. So I was wondering if for your model future projection for the 250 million years, were there any marine, biogeochemical cycling incorporated in the model?
Thank you for that great question. The answer is no. We didn't do any biogeochemical modeling in the ocean. We have the capability to do that. We have a biogeochemical model that works for modern Earth, but definitely we'd have to retune that for any kind of future projection, and we'd have to make a lot of assumptions because, as you know, the parameter space goes into regions which are vast and unexplored and highly unknown. So we'd have to do, I think, an ensemble of runs to get a feel for how things would change. But thank you very much.
Thank you. Yeah.
All right, we have about 4 minutes left. So we do have a couple of online questions for some of the previous speakers we could cover if there aren't any more in the room, or new questions for the current panel. Go ahead.
Again, Bumsu Kim from NASA Johnson Space. For the third speaker, so currently I was wondering, since a lot of organic geochemists, one of the challenge is, when we see an organic compound, how can we distinguish between biotic and abiotic process? So, was it for the machine learning speaker? I'm sorry. So I was wondering, let's say I found amino acid in this mid-ridge like sediment. Of course, they are like very conflicting. I mean, it could be produced biotic but abiotic, as you are aware. So I was wondering how machine learning can help distinguish, and like what are the parameters that really need to kind of help this learning? So
yeah, thank you for that question. So I didn't get a ton of time to explain the nature of our data set, but we, in the abiotic samples, some of them include non-biogenic organics like microbial substrates, but no microbes. And we are, like in our paper, we talk about biotic mimicry, which is geochemically complex environments mimicking biosignatures. And so that's what Bethany intentionally tried to do with her data. We do need more complicated data under non-Earth temperature, pressure, and including rocks in those. So none of our experiments have rocks right now. And I think that's going to be key because truly like a lot of fractionations that you see that are in biotic range can also be explained by abiotic processes.
So does that mean like more abiotic experiments done and then looking at, these are from abiotic will give a more database, right? Is that?
Yes, yeah, both abiotic and biotic, both.
All right, okay, cool. Thank you.
All right, we are 2 minutes away, so I think we'll take the prerogative to thank everyone, all of our speakers and all of our attendees today, both in person and virtual. This has been a really enlightening session, so let's have one giant round of applause for everyone. We would also like to remind you all that our follow-on Astrobiology and Exobiology session 2 will be this afternoon, starting at 2:15 p.m. Central Time in this room as well.
Make sure to stay for the whole session because at the end, I'm going to have a video of a protein that folds using just salt water. You're not going to want to miss it, you guys. Also, I wanted to generally just remind you guys tonight is the eye poster session. I know like they're generally not as appealing as the regular posters, but a lot of the eye posters are astrobiologically related. So I would highly encourage you to view those online and reach out to those people as well.
And I'd just like to also thank Shelby, our moderator, as well as Denise and our technical team in the room. Thank you so much for making this a very flawless session. We appreciate you. All right, and Denise, we'll leave it to you to close us out.
And the only person or people left to thank are all of the attendees. So it was really great to see such a great turnout, even from online. I could tell that the room was almost full. And for a early morning session, that's really awesome to see. We all are super interested in the search for life beyond Earth. And so it's awesome to see this cool field gaining traction at LPSC. So I'll see you guys at the session this afternoon.
Thanks, everyone.
I'm going to run and catch Lily real fast, okay?
Oh, yeah.
I got it because I'm a computer scientist like her.